All right, so I think we're ready to start. Thank you everybody for joining today at the first day of the conference. I think many of you may be jet lagged. Some of you who are locals here in Europe may be fine, but thank you all for joining. And I'm really excited to be here in the third edition of the Creative Video Editing and Understanding workshop. I'm so happy because this is going to be the first time we do this workshop in person. We started this workshop like 2 years ago, and we have been doing it virtually. But this is the first time that many of my co-organizers and I are here actually hosting it in person. So I'm really excited about the workshop today. To give you like a sneak peek of what the workshop is going to be about, I'm going to play a video. It's a trailer video that summarizes the workshop and also the AI Film Fest that we're going to be hosting today in the afternoon. Right, so hope that's exciting. Like I've been working in similar topics of video generation for some years, and I know many of you have been working on those. So even being able to see these videos, like nowadays, it may seem that these videos are not super high quality, but it's a very big jump from what we were able to generate even 2 or 3 years ago. So it's excited to be here today, different speakers talking about this video generation topic. But we will also have speakers talking about video understanding and editing as well. Of course, like this won't be possible without the help of a team of organizers. Like we like to thank them all for their hard work and making this workshop possible. So some of them are here with us in person. Others couldn't make it due to visa reasons or personal reasons. But thank you all for your hard work. I would like to highlight especially Anyi, who actually keep us all organized. Who actually made sure that everything was ready for the workshop as well. Thank you, Andy, and thank you all. Right, so just to start a bit of the workshop with a bit of motivation. So I really like this phrase from Hugo Caselles. I hope I'm pronouncing his name correctly. And he said, like, the universe is made of a story, not of atoms. So, of course, you will actually doubt this phrase, but in the deep meaning of this phrase, it means really that the stories shape our meaning of the world. And it is important to actually understand the stories and be able to create stories and tell stories to everybody else. And this is a big motivation for this workshop is how can we actually bring together technology to help people create video stories and to help them tell their stories to the world. If we go back in time, like from the beginnings of video storytelling, I think we definitely have two different streams of evolution. So on the top, we see the evolution of how people is capturing videos. So starting from the iconoscope in the 1920s to today's digital cameras, like everybody or many of us will actually have a phone that will have a video camera recording. So we have seen how these video capture devices have become widespread available, and everybody can now capture video. A similar thing has happened to video editing, right? Like at the beginning, people were cutting film with scissors. It was a very tedious process until today, where we have, for instance, like non-linear digital editing. This is still a very complex. Those are still very complex software to use, but it has improved over time, and it has opened the door for other people to tell their stories through video. But a big motivation for the workshop is how these two different streams of evolution will change in the realm of AI, right? So we know that technology is getting mature for many practical use cases. So Now the question is how video capture will change having available AI technology that can generate and edit existing video, and as well how video editing will change once we have AI-assisted editing. And one thing to keep it central to the workshop is like, it's not only about AI, and as we will see later, we bring researchers from different communities like human-computer interaction and also psychology, because it's not only about automated generation, it's more about human-centered generation, right? Or human-centered video storytelling. And as you know, this is the title of the workshop, AI for Creative Editing and Understanding, but I think it will be more relevant in the realm of today's state to rename the workshop a bit into AI for Creative Video Generation, Editing and Understanding. As you will see today, we'll have different speakers talking in different aspects of these areas. As I said before, like really what we wanted to do is empower the new wave of creators to tell their stories. We know that we have widespread availability of digital cameras. We now have emerging AI technology that can generate and edit video. And the question is how these technologies will actually encompass together, right? Like how a creative video maker can leverage AI, and how a creative video maker can leverage as well existing tools to create and tell their stories through video. And again, like just as a reminder, like one of the workshop goals is to actually bring people from different communities, from the HDI community, from the machine perception community, and psychology and artist community, to work together towards making these technologies usable and applicable in the real world. With that, I will actually hand it over to Anyi, who's going to give an overview of the workshop.
Hello everyone, this is Anyi, and I feel excited to introduce the program of our workshop. It includes several great keynotes from researchers, professors, artists, and also from industrial. And we will also host a panel discussion among them, and in the afternoon we will have film session and our technical paper session. So as a highlight of this year's program, we initiate the first the film session. So we received 49 films in total, and it comes from 15 countries like Spain, Finland, USA, China, France, and a lot of other places. And we will announce its awards in this afternoon's session. And we will also show some great works from the creators. And our technical paper submission has increased a lot since its first launch in the first edition. It's almost like it's doubled. And when it is substituted in proceeding and extended extracts, it also gets doubled. And we will announce paper awards in this afternoon's paper session, and also showcase a lot of oral session, and the authors, they will come in person to show their great work. Of course, all of this is made by the great work done by the paper program committee, all of them, and we thank for their great efforts. And also in this afternoon, we will announce the outstanding reviewer in the paper session. And our workshop is funded by these two great sponsors, the COUT and also the P Collabs. So thanks for the fundings. So in the end, I will give an overview of today's program. So in the morning session, we basically have a lot of keynotes and also a panel session. And in the afternoon, after the lunch break, we will have our first AI Shortfest Film Festival, and also include a technical paper oral session. After the coffee break, we will have another 3 keynotes for industrial and artists. And I hope all of you will enjoy today's workshop. Yeah. I think now I'm going to welcome our first keynote. Yeah, and it's Professor Marc Christie. He is an assistant professor of University of Rennes 1 and a member of IRIA. His research interests focus on smart tools to assist the creation of complex 3D content by mixing computer graphics and artificial intelligence techniques. He is also the keynote of our first editions in ICCV 2021. So let's welcome Professor Marc.
Thanks for a very nice introduction. Okay. Hi everyone. It's a pleasure to be here. It's a pleasure to open this session at CVEU. I would like to thank the organizers for the great program, and it's so fun to see how things are evolving fast in the field. Okay, so what we're going to talk about today is trying to better understand style in movies and see how we can exploit this stylistic information in generating content. And on the right, the picture is just a sort of stable diffusion as a researcher intensely watching movies to try to understand style. I think it was a fun picture. So style, as you know, is a fundamental dimension of movies. It's the dimension that's bringing the artistic value to the content and, of course, the value to the filmmaker. It's so important that students in film schools, the first things they're going to work on is replicating style of famous movies. So they would do like à la manière de, they would take some famous movies and adapt the style of these famous movies. So it's a fundamental dimension, and it's really interesting for us as researchers to try to understand the stylistic dimensions so that we can then export it, model it, and transfer it to other types of contents. So, of course, in the movie industry, I mean, people have been using a lot these stylistic aspects, and they've been driving their. Oops, if you look at this. And they've been driving their content by already existing content in the past. So essentially, taking inspiration from other filmmakers to exploit, reproduce, and adapt this content. And it's a process that is not that easy, because you can't do just a direct transfer like of the camera trajectory or of the lighting aspect. You really need to see how this can be adapted or in a way generalized, and we'll talk about it later. So, maybe we need to define style in cinematography. So I wanted to get this super fancy definition of style by a famous filmmaker, but actually the Wikipedia one was not too bad. So what is style in cinematography? It's recognizable cinematic techniques used by filmmakers to create specific value in their work. So it's including sound design, mise en scène, dialogue, cinematography, edition, or direction. And I think what the word that I highlighted here is recognizable. So when you're creating a content, it can only get some value if it's recognized by other people as something valuable. And as you see, style spans over a number of cinematographic techniques, and you could display these techniques in a sort of n-dimensional space. So you would have lighting, you would have cinematography, you would have the editing, and each movie would be a point or maybe a trajectory inside this n-dimensional space, because in some movies you would change style between different parts of the movies. But in all cases, you've got this field representation. You've got this complex multi-dimensional space in which you can plot the movies. And there are many interesting questions here, which means, okay, does it mean that if there is no spot in the space, there is no style? What does it mean to create some content that is between these styles? And this is maybe because there was no movie created using this style. Does it mean that we don't have enough creatives to do this? Or does it more fundamentally mean that some combinations of techniques are valuable and others are not? And this remains an open question. So what I'm displaying here is just it's a joint work with Jean-Peïc Chou, which is here, and it's displaying tropes, film tropes, which are visual and narrative structures inside the movie and help you to understand how the same genre, so we can take comedy, for example, in Blink, and how the same genre can spread over different stylistic aspects. If we have a quick look at the past, my understanding of style in 2015 was fundamentally this idea that we had a bunch of here 25 cameras, and from these 25 cameras we tried to optimize the editing of the sequence that would fulfill this equation. So we tried to optimize this equation where the idea was to say, okay, we want to select what is going to be the best shot. Okay, this is the action quality, so it's the shot that fulfills the most, that reveals the most the quality of the actions that are ongoing. It's also the transition cost, so you've got multiple shots and you want to cut between shots. There are many rules that you use to cut between shots. And you've got the rhythm cost, which represents the pace at which the camera is cutting. And using this, taking as input a 3D scene and set of actions, then we had this ability to automatically choose the cameras and edit the sequences together. And we said, oh, that's fantastic, because here we have some weights, okay? And these weights could be used as a representation of the stylistic dimension, meaning that just playing with these weights, you can have a very fast-paced, slow-paced, and you could combine the different weights you wanted. So we said, that's fantastic, and we showed results to people, probably like you and me, doing some rough video edits that find it not too bad, and we showed it to professional editors that said, oh, that's really awful, saying that we were far from the target of really reaching what editing is. So it's at the time we didn't use deep learning to try. It would have been an idea at the time to try to decide what were the weights automatically by analyzing movies. But at the time they were not as evolved techniques as today. So we transisted. We wanted to look more recently at how we did this. We used ResNet applied to short film clips, so 16 frames. So we took film clips, made these chunks, run ResNet on it, and tried to perform a classification with a number of famous movies from filmmakers. And we thought that we would be able to extract some aspects of style. And what this revealed, actually, is that here you have the filmmakers with the different colors, and this actually revealed that the clusters were more representing not the style, but just the dates at which the movies came out. So the visual artifacts that you would have in regular film cameras compared to digital cameras, so it's very low-level features that are actually handled here and are not enough to really compare style. And this can be also shown because some filmmakers, they have a consistent style, while actually when we display this in a TSCE representation, you can see they're quite far apart. That helped us to say, okay, we need to look at more evolved stylistic features. And with some colleagues, we looked at aspects such as the depth of a shot. You can have very shallow shots or very deep shots in terms of how things are arranged in a sequence. And that's a very interesting feature that has not really been studied today in video analysis. So for this, we simply used some depth estimator techniques to get depth maps. And then from these depth maps, we performed some temporal smoothing, and by running a K-means, we were able to identify in the shots what was the first part of the shot, so closest, the medium, and the background. So just by deciding the number of K values you want, you can extract these features. We also looked at a bit more closely at how to extract motions, camera motions from movie clips. So it's a long-standing problem, and though it works really well in the computer vision field on regular, like robotic videos made by robots or perfect cameras, when you're looking at cinematography, the problem is much more difficult because you have lots of artifacts like depth of field and motion blur, which prevent classical structure from motion techniques to be able to understand the motion. On top of that, the content is very often dynamic. So the camera is moving, the characters are moving at the same time, you have the cars moving, and this is very confusing to estimate properly the camera motion. So here we devised a technique that was using some optical flow features, and through the optical flow features, we then computed an angle grid, so basically deciding in which area of the screens were the angles different in terms of visual motion. And from that, we fed it to MNP, and that would give us a quite good estimation of the motion inside the movies, despite issues like motion blur, depth of field, or other artifacts such as moving characters. So from this idea that we needed to extract more high-level features, we here worked on trying to learn camera behaviors. So camera behavior is what we define as a correlation between the motion of characters in the scene. So you can see here the skeleton extraction of the characters relative to the motion of the camera. So actually how the motion of the characters is going to trigger the motion of the camera, and what's the relation between them. So what we did is that we analyzed the number of movies, and we built a latent space of these correlations. So then, given a new movie clip as a reference, we could draw, or we could compute the path in the latent space of these correlations, and then have a generative technique that would sort of reproduce the stylistic aspects in terms of visual composition and in terms of relative motion of the camera from the reference clip to here the target clip. Okay, so that worked quite well, but we were actually only thinking about the correlation between the characters and the camera, and we were not looking at how the camera is moving in relation to the background. So we then had this idea of trying to extract the motion of the camera in relation with the background, but also in relation with characters. And it's important to have it in relation with characters, because in movies, people will often use characters as anchors to turn the camera or to move the camera around. And what we proposed here is to try to transfer a number of stylistic features. Our idea, more specifically, was to see whether, from the film clip which is on the right, whether we could transfer the characteristic of this film clip into a nerve-based representations, which is a neural radiance field representation, where you can encode the movie in MMP, the scene in MMP representations. So if you do traditional, and that's what we did in the paper, you can go check the details. So if you try to apply only structure from motion techniques on the left shot and retarget that to the right shot, it's going to fail in a number of cases. I mean, due to the artifacts we were mentioning. So what we did here is that since we have a nerve-based representation of the scene here on the left, it means that given a camera and given a number of parameters, we can render the scene. And this is a differentiable rendering system, getting from the cameras to the 3D representation. So then, for each frame, we can compute what are going to be the differences between the reference clip and the generated nerve camera pose. Given these computed differences, we can then back propagate this information through the network, because this part is actually differentiable, and that's the high added value of the nerve-based representation. So the question is, okay, we can compute the differences, but what differences? What do we want to transfer? And we propose to work on two visual features. So first, character poses. Character poses, as I was saying, is very important to anchor the camera for the filmmaker, so we can detect both in the real movie the poses of the characters. So here it's confidence heat map, driven by some pose detection techniques, and we can compute it both in the real movie and from the nerve-based, so the synthetic rendering. And then we can compute a loss, so rather than using a pixel loss here, we use the passage time distance, which was better at spatially, at driving the network so that the points could overlay in space. Just as a quick illustration of this, comparing photometric loss and our pose loss, here we had a reference scene, which is this scene. We had a target scene, which was exactly the same scene. And we showed that if we use just a photometric loss between the two, the field, okay, is not that easy to compute. So if we want to compute the displacement of the camera in X or Y dimension, this field is not that easy to optimize. Well, in this case, it's not too bad. But if you want to apply the characteristics from this shot to a completely different shot, and you would use pixel comparisons of photometric loss, well, then you see the space optimization is very difficult. So there's no clear gradients, meaning that you can't move the camera to get to fit the poses together. And we showed that our pose loss displays a very nice gradient space in which we can optimize. The second visual feature we used was optical flow, because if you remember, we wanted to transfer the idea of the camera motion, not precisely the camera motions, because the scenes are never going to be the same, but the flow of motions. And here we just use a differentiable network to get the optical flow from the original film clip and the optical flow from the nerve-based scene, and we had loss to compare both. So we took these features, we put them together in the system, we ran it, tried to optimize, and it didn't really converge easily. And that was essentially because there was a lot of information. Since we were comparing images together, frame per frame, there was a high computational cost. And not all the regions inside the image are interesting for the computation. So we added an extra component, which is a guidance map. So it's like, it's a way to really help the system, the network, to focus on specific parts of the image. So here we used a Gaussian sampling process where we included a number of the feature points that were extracted from the body poses. and a number of features of the scene where there were significant motions. So that gives this overall process where you have the cameras on the left, the reference views, the original film clip, the rendering of the views here, and we have the two losses that were combined into this guidance map that helped the system to converge. And what is interesting here is that since the whole process from left to right is differentiable, well then basically it gives us a gradient, that we can use to exploit. So we can compute what are the changes we want to apply on the camera angles so that we minimize the losses. Okay, so some results. I mean, this is the famous dolly zoom effect that you know from the Jaws movie. I hope you're big fans here. And this is the dolly zoom process applied, okay, to two different scenes. So, if you know the dolly zoom technique in the movie industry, the dolly zoom is pushing in the camera while you're opening the camera angle at the same time, or pulling the camera while you're closing it. And this gives this widening effect. So it's well used in the movies. It's a famous reference from the Vertigo Hitchcock movie. So of course there are artifacts here. You can see the hat of the guy, which gets a bit pixelized, but that's because there's not the same depth here in the synthetic scene than what we had in the original scene. Okay, I'll just go through a few examples here. So results on different film clips. Okay, so you've got some fast zoomings, you've got some, at the bottom, you've got some noisy and shaky, you can see here. So noisy motions that can also be transferred. This is a very slow pull out, okay, that can also be transferred. I don't know why this is the picture cycle. Okay. So here what we did until now is just optimizing well the lens of the camera and also optimizing the position of the camera. But we can optimize other parameters. And what we try to do here is to see how it could work with dynamic nerves. So dynamic nerve is encoding inside the nerve, not a static scene, but a dynamic scene, typically where you would have characters moving. And what we can do here in the retargeting process is not only choosing the camera angle and the length, the focal length, but also choosing and optimizing the timing of the characters, so the speed at which the characters would be moving, so that it perfectly fits the composition due to the character poses and the motion of the camera. So also as a sort of a fun test, we had this idea of seeing whether from an original film clip we could transfer it to a synthetic environment, not a nerve-based environment, but a 3D CG environment here based on this Unity rendering, for example. So what we had to do is we took this 3D computer graphics representation and we transformed that into a nerve-based representation, and we used our JAWS system to here transfer these characteristics into the nerve-based representations, and once they were translated into the nerve-based representation, then we could have a trajectory in this nerve space, and the trajectory in this nerve space could be re-exported to the Unity environment to perform a high-quality rendering. So it's transferring this film content directly to this CG environment through the nerve-based representation. Okay, so that has really opened the space for research on our topic, because we believe there's much more parameters on which we can work. So widening the problem, the idea is that we could probably think of relighting techniques. So not only can you transfer...
Welcome to ICCV 23. We are sorry for this queue and thank you for your patience.
Okay, thanks. So we are going to... so yeah, the idea is that not only can we transfer the camera characteristic, but we can transfer lighting. Why? Because now we start to have relightable nerves. So nerve representations in which people would encode and be able to control the lights. So in that case, well then we can add an additional dimension in the loss metrics, which is a measure of difference in terms of lighting quality, whether it is histograms or many other ways. So we could also transfer the lighting to a nerve-based representation, and that's a topic we want to address. Of course, as things are progressing quickly, we're seeing nowadays ways that people can extract body representations from movie and body animations from movie. So we could also use this information to retarget in the nerve representation the character poses. So not only would you transfer the light, the camera motion, but also the poses of the characters, or try to adapt the poses of the characters so that the nerve-based representation is as close as to the original. Many things, I think there's a lot of potential in this. But if we take a step back, I think what we're doing currently is actually only looking at the output of the movie, which is style, okay? We analyze the video and we try to understand style from the videos. But if you look a bit at the literature, the style is actually driven by the meaning, okay? And you want to add this dimension to the process to be able to try to better understand style. You can't use any style with any type of content and with any meaning you want to give to the content. So these aspects must be studied at the same time. And of course, one of the issues is that, well, when you get the movie, you don't have the meaning that the filmmaker wanted to put in the movie. So that's a rather complex task. And taking another step back, it's also about the intentions. So a filmmaker has a number of intentions in creating the content. And from these intentions, he's mapping these intentions with narrative structures and with the stylistic aspects. And if we want to understand the style, well, then probably need to go back to what were the intentions. So there's a lot of literature on that, and there are some great resources. So multimodal film analysis, how film means, by John Bateman, and this is a really valuable resource if you want to understand the discourse structures and how the discourse structures of movies are related to content. And of course, David Bordwell's on the history of film style that gives a lot of insights on that. And to conclude, I want to thank these great guys for the work behind these contributions. So Jean-Peïc, Chou, Romain Courant, Shi Wang, and Christophe.
Yes, thanks so much for... If you have any questions, please raise your hands and I will hand over the microphone to you. Yeah.
Thank you very much for the interesting presentation. I was wondering if you have considered using action recognition style of features for your characterization.
Yes, so we thought multiple times about action recognition in movies. In many cases, it's very hard to get a precise result out of action recognition. It's very simple when you're sort of jumping, running, talking, and then the results are very precise. But when you're going into more subtle contents like changes in the facial and the attitude, changes in the postures, and very small type or fine-grained actions, then it gets very difficult. And actually the camera is really related to these fine-grained actions. So we probably need to have a more better techniques for the action detection that could be able to go at this level.
So thanks again for Professor Marc.
I have just one question. Since he asked about action recognition, do you think that encapsulating information concerning the editing, like how every single shot is concatenated to the following shots, would be helpful to determine action recognition or any other movie editing context?
So
basically taking into account movie editing patterns, basically like how the shots are concatenated.
So that's both an easy aspect because it's going to give the contextual dimension, and it's also a very difficult aspect because in a number of cases, the cutting, there are some time ellipses in the cutting. So basically there is an action, you're going to cut, you're going to cut and you're going to cut 2 moments times later. And these ellipses are filled in because we have the knowledge of what is happening, but of course the computer cannot really derive this information. So it's possible to use that information to some extent, but may fail with temporal ellipses, which are quite well used.
Thanks.
So, thanks again for our great presentation. And digital art analysts. Let's continue to our last speaker. It's my pleasure to introduce Maneesh Agrawala, and he is the board professor of the Institute for Media Innovation together in University, and he works on computer graphics, human-computer interaction, and visualization. His focuses on investigating how cognitive design principles can be used to increase the effectiveness of audio visual media, and he is in Heilbron and an ACM fellow. And let's welcome him.
So let's see. First, I want to thank the organizers. This is it's fantastic to be here and present at the Creative Video Editing and Understanding Workshop. I agree with the organizers. Generation should also be in the title. Today, I wanted to talk with you a little bit about AI interfaces. And if you'll bear with me, I want to step a little bit away from video. A lot of the examples that I'll show won't necessarily be a video, but I think you'll see how the things that I talk about today relate to video. And I think they're certainly related. I also wanted to have a bit of a provocative title, so really to engage you all in the discussion. And so I hope there will be some questions at the end. So unpredictable black boxes. Maybe we should unpack this a little bit. So let's start with this. This is a black box. And modern AI, especially generative AI tools, are essentially black boxes. They are tools that take some input and somehow magically transmute it into output. Now in this case, the black box represents value, but really it could be any modern generative AI tool. It could be GPT-4, it could be ChatGPT, it could be Midjourney, it could be Stable Diffusion, it could be Gen 2, it could be any of these. and they are all essentially black boxes. So for a long time, I've been wanting to change the profile picture on my webpage. It's really badly out of date. So I decided to give the following prompt to DALL-E. And this is the result that it produced. Now, I don't know about you, but I think that this image is amazing. Right? It made a coherent photographic image from a text prompt alone. Right? It figured out that this person is probably of Indian origin from the name. It dressed him in professorly attire. It put him in a conference room, a good location for a professor to be in. The low-level properties of this image are also very realistic, right? The lighting and the shading, they all look really, really good. It works as a single unified image, and this is just stunning. Now, it does have some artifacts. I won't quibble about these. The fingers on the hand are not looking quite like a real hand. One of the temples of the glasses is missing. And I was really hoping that that DALL-E would make a cooler, younger image of me. But, you know, I just want to stress how amazing this really is. We can now generate high-quality images as soon as we can think of text prompts. And this is a new capability, right? We, as humans, have never really had this capability before. So it is absolutely amazing. All right, so let's use this tool, DALL-E, to make another image. In this case, I want to take the main quad of Stanford, where I work, and it has this beautiful memorial church in it. It's a big, wide open quad space, and I want to render it in the style of Blade Runner, the film. Right? And when I think about Blade Runner, what I really think about are nighttime scenes with lots of rain, neon signs all over the place, food stalls. It's downtown Japan. It's gritty. That's what I think of. And here are some images. So on the left is a film still from the film Blade Runner, and you can see that a human photographer was able to create this image in the Blade Runner style. And all of this is to say that there is a kind of recognizable style that people can certainly create to represent Blade Runner. And what I want to do is take that image that I have in my head of the main quad at Stanford and Memorial Church. If you haven't visited, come visit us. It's a beautiful place. I want to take this and put it in that Blade Runner style. And I'm going to do this using DALL-E. And so, here we go. So this is the first prompt that I try, and it gets it to be nighttime, there's neon, but I can't really see the main quad and the palm trees. It doesn't really look like Stanford. So a couple of iterations later, I now get the main quad. The neon has kind of gone away. It's not really rainy. There aren't any food stalls. So I continue to iterate. I adjust the prompt. And now it just looks like a rainy version of the quad. It doesn't really look like downtown. So I continue my iterative process. And here we still don't have that grittiness of the downtown. There's maybe a little bit more activity happening. You can start to see some of the tents. Maybe those represent food stalls. There isn't a lot of neon. It still doesn't really look like Blade Runner. So I asked for an illustration. I figured this might give it some more flexibility. At iteration 21, I end up with this. And you know, to me, this doesn't really capture what I had in my head about the Stanford quad in the style of Blade Runner. And it took me hours to get to this point, right? Lots of random poking around with prompts, trying different things out, not ever really achieving the result that I wanted. And what's worse is that I don't know how to push the imagery, how to iterate towards something that's closer to what I want. So it feels very, very random. And this, to me, is a terrible interface. Okay. And I just want to point out that prompt engineering is known to be so difficult that there are now websites where you can go out and buy good prompt templates. So this is from Prompt-Base. You can pay $1.99. You'll get a prompt that hopefully will get you something good. And there are, of course, lots of research papers, a whole cottage industry of research papers that are all about prompt engineering. And you know, to me, these feel a little bit like random hacks, right? Someone has gone out, spent a lot of time trying to figure out some prompts that seem to work, and then they've called the resulting prompt template a prompt engineering prompt. There aren't really deep principles to finding these good prompts. So why is using these kinds of AI tools and models so difficult? Why is prompt engineering so difficult? And I think the key issue has to do with the user's conceptual model of these AI tools, or the lack of such a model. And to really understand this, I think it's instructive to look at an anecdote from Don Norman's classic book, The Design of Everyday Things. I'm guessing that most of us in this room have read this book. It's a very well-known book. If you haven't read it, I strongly recommend it. It's very easy to read. And in that book, Norman describes this story about a refrigerator he used to own. It has two compartments, a freezer compartment and a fresh food compartment. And and there are temperature controls, one for the freezer, one for the fresh food. And Norman had a lot of trouble setting the temperature for these two compartments properly. He would adjust the dials, and he was able to get the freezer to be cold enough, but then the fresh food would be too cold. And when he got the fresh food just right, the freezer would be too warm. The problem here is that Norman had the wrong conceptual model for how the controls adjusted the temperature. Okay. In Norman's model, there are two cooling units, and one of the dials adjusts the cooling unit for the freezer. The other adjusts the cooling unit for the fresh food compartment. These are independent controls, and it turns out that this is the wrong conceptual model. It didn't allow him to properly predict how to set the temperatures. The true system model is the one that I've shown here. So there's a single cooling unit, and there's a dial that adjusts the temperature of that cooling unit, and there's a second dial that directs the cold air with a valve to the freezer or to the fresh food compartment. So the two controls are coupled in this way, and this is very different from the conceptual model that Norman had. And the result of all of this is that Norman didn't have the correct conceptual model. He couldn't predict how adjustments to the controls would lead to the output temperatures. And for him, this was really frustrating because every time he adjusted the dials, it would take 24 hours for the temperature to stabilize in the refrigerator. And so every iteration took a full day. Right? So this is terrible. Right? And so well-designed interfaces really let users build a conceptual model that can predict how the controls, how the inputs will affect the resulting outputs. And when the conceptual model is not predictive, interfaces require trial and error. That's the only thing that users can resort to. They have to just try. And this is very, very frustrating. Now, one thing I should point out here is that the conceptual model does not need to match the true system model. It just needs to be predictive of how the inputs will map onto the outputs. And finally, it's our job as AI tool builders, as designers, to build interfaces that let users predict how the inputs map to the outputs. Okay? So it's on us to do this. All right, so let's go back to DALL-E. I decided to try and adjust the prompt to get a cooler and younger image of myself. This is what it gave me. All right? But it's really unclear how this result reflects the prompt words cool and young. Right? Do those words, how do they lead to the sports code, maybe the loose hair? I don't know. What in this image represents cool and young? And so without a predictive conceptual model, I'm just stuck with trial and error. Now, you might argue that one goal of AI is to build tools and interfaces that are indistinguishable from humans. And you might say, well, isn't natural language the way that one would interact with another human? And of course, humans are great interfaces. Right? Humans can do lots and lots of things if we work together with them. And one thing I want to argue is that humans are terrible interfaces as well. And this is for exactly the same reasons that AI are terrible interfaces, right? We don't have a really great predictive conceptual model for what another person would do given a natural language prompt. Now, all of that said, working with humans is still better than working with AI. And that's because we can have conversations with other humans to help us produce the desired result, to iterate towards the desired result. And the conversation lets us define what we mean by various terms and ask questions when things are unclear. So here, I'm working with a human artist, and he asks me if cool means wearing a sports coat or wearing a hoodie. And I suggest maybe it's something in between. And this allows us to eventually reach this final result, which is maybe a little closer to what I had in mind going into this. So working with humans is easier than working with AI because I think we have a prior conceptual model for what the other human will do based on a model of ourselves. We imagine what we would do given a task prompt, and we assume that the other human will do something similar. Right? And, you know, that's not a perfect model. There are lots of places where that breaks down, but it also is better than the model that we have for AI. In addition, we have this conversation, this ability to converse with the other human, and that lets us build common ground, a shared understanding of what the task really is, and it allows us to repair when there are misunderstandings or ambiguity. And that's really, really important. But I want to point out that the conversation can often take a while to really establish that shared understanding. It can take lots of back and forth. So some of this turn-taking is still involved. For teams, it can take days, weeks, months, even years to really build enough common ground to work efficiently as a team. So the turn-taking and back and forth is not ideal, but it's better than with AI because both parties are working together to reach a shared goal. Now, with AI, a conceptual model is either non-existent or it is incorrect. We have this tendency to anthropomorphize AI it's really hard for me, and I think for many of us, to talk about AI and what they're doing without saying that they are thinking something. Right? We say this all the time. And then, as users of these AI tools, we build a conceptual model that is based on what a human would do, given the prompt. But it's very, very unlikely that an AI is thinking the way another human thinks, right? And so our conceptual models are often incorrect. And these black boxes typically require a lot more iteration and trial and error in order to reach the result than working with a human. And what's worse is that the iteration rarely feels like a shared refinement towards an end goal. Right? So these are some of the differences. Now, how can we make these AI black boxes better? Well, one thing I think we might want to do is to move them further in the direction of humans. We might want to make them a little more conversational in the ways that humans are. And we collectively in research are doing this. And so I want to show you some examples. So tools like Dream Booth, this is from Kfir Aberman and his colleagues, he'll be speaking later today. I don't think he's here right now, but if he is, say hello. So this work is fantastic, and it's really, to me, an example of establishing common ground between the human user and the AI system. So as a user, I give Dream Booth a few example images of what I mean by a particular dog, and Dream Booth fine-tunes the weights of an underlying AI model to learn what I mean by the concept of this particular dog. And then Dream Booth can stick my dog in other scenes. Right? So we've worked together to establish the meaning of this dog. Here's some more work from Kfir and his colleagues. This is on prompt-to-prompt editing. This one, to me, is really about repair. So here, suppose I initially prompt the model for a castle next to a river. The model produces a perfectly fine image for that prompt. But what I really wanted was a children's drawing of that castle. Well, I can repair the prompt and get the desired image. So this is really, really nice, right? This fits the conversational model much better. And I think a key feature of this method is that it qualitatively keeps the structure of the edited image similar looking to the initial image. It's not exactly the same, but it's pretty close. And so this supports a kind of iterative refinement. Here are some more examples from the paper. And to me, iterative refinement really involves three main components. Actions need to be incremental. So small changes to the prompt lead to relatively small changes to the image. And this is in contrast to interfaces where if you change the prompt even a little bit, the image changes drastically, right? So it doesn't really feel like iteration and refinement. Action should be reversible. We can build that in pretty easily by just maintaining an undo stack. And the feedback updates to the image after changing the prompt, those should be fast. And I believe this technique takes on the order of a few seconds to update the image, which is pretty good. But I think we can make this even faster as well. And many of us are working on this. Now, another direction that I think is really exciting is neurosymbolic methods. And the idea here is, given a prompt, the AI black box should synthesize code, which is then executed in order to generate output visuals. And the advantage of this approach is that the output program here in the center is something that both humans and AI models should be able to understand in a similar way. So code can have formal semantics, and that is understood by the underlying machine, and it is also understood by a programmer. But even without formal semantics, the human developer might be able to inspect the resulting code and check that the code is doing the right thing, so we get interpretable results. We also have the ability to go in and debug the code. We can tell the AI that something is wrong with the code. We can just manually fix the code. So there are a number of ways in which this kind of approach is much more useful, I would argue, than simply directly producing the final result. And at one level, I think this approach is about shifting the language for communicating with the AI from being purely natural language to being some combination of natural language and code. Right? And so I'm pretty excited about this direction, especially with the idea that users could specify the underlying code primitives and the grammar for the language. Right? This will allow the system and the user to work at the same level of abstraction because I've defined the abstraction through the code primitives and grammar. Okay, so the last thing I want to talk about here is dealing with the ambiguity of natural language. And so here's an image. This was generated by Stable Diffusion, and I want you all to think for a moment about what the prompt might have been to generate this image. Okay, you have it? Everyone with me? Good? Okay, so how many of you were thinking this? All right, many of the best images generated today using tools like Stable Diffusion have prompts that look something like this. And notice here that the prompt asks for a full body. We get a full body, I think, mostly. It asks for a walking pose, right? I don't know, I don't think this is really a walking pose. It asks for slow motion. This isn't really slow motion, I can't tell. It's like there's slow motion in some ways. It asks for a female Spider-Man wearing a full bodysuit, light silver armor. We get some of that, not all of that, right? So a lot of the prompt isn't directly reflected in the image. But what I really want to focus on is that natural language is not well suited for describing precise spatial composition and pose. So often prompts will be fairly ambiguous about these aspects of the image. Right? They're left to the AI to generate. We don't say a lot about how exactly Spider-Man should be posed. And any small change to the prompt changes the image composition completely. If you use basic Stable Diffusion without tools like prompt-to-prompt editing, you're going to get a very different image each time you change even a word of the prompt. So you don't get this iterative refinement. All right. So earlier this year, we, and by we, I really mean my grad student, Jen, who unfortunately couldn't be here today because of visa issues, developed ControlNet. And the idea is, instead of using a text prompt alone, is to provide conditioning imagery. And that conditioning imagery constrains spatially the images produced by a text-to-image diffusion model. And so here we're using canny edges. Those are our controls, our control imagery. And when we feed that to ControlNet, it's able to generate these high-quality images, but ones that really match the spatial constraints imposed by the control machine. Now, this is without a text prompt, but you can also use ControlNet with text prompts. And these text prompts provide more global controls over the look of the image. But we're still spatially constrained by the image images. And you can change the text prompt, and you'll get very different looks. But again, the overall structure, the composition, the poses still match. And we can use other control imagery as well. Here at the top, we have MSLB lines. You can, depending on the prompt, you can get outdoor scenes or indoor scenes. Pose, get very different people, 2 different versions of a chef. Some more pose, you can have a dancing woman or Michael Jordan playing basketball with the same pose, just different prompts. You can have, you can use semantic segmentation, get a variety of outdoor scenes, and you can of course use sketches and get lots of different imagery depending on the prompt, the text prompt, but all constrained to have the same structure. So, some takeaways. Well, first I should mention, if you want to learn more about how control net works, we'll be talking about it later in the week. So come to that. Some takeaways for this talk, though. When users cannot predict how input controls affect the output, the interface is terrible. And this is true of black box AI, it's also true of other humans, and it will always be true until we, as tool designers, can provide predictive conceptual models to our users. Now, we can improve AI interfaces, and we can do this by providing tools to establish common ground and repair. We can enable iterative refinement, we can use code as an intermediate language, and we can allow visual inputs and controls to deal with the spatial ambiguity of language. So think about this in the context of video. I think there are lots of opportunities for us to do some of these things to our video editing and generation tools to make those better. And with that, I want to thank the people that helped me put this talk together. If you want to know more, come check out the work that we're doing. And I think we can take a few questions.
Also on top, and we have some time for a few questions from the audience. Please raise your hand if you want to ask a comment.
So you talk about, human language as the interface, code as the interface. What we also know is if you do some parameters or well-defined, you can control the inputs more. To give an example, for 3D models, we used to have pose, shape, and so on, very granular things which we can then control to get to the output. And I know it's not possible for generic videos, but have you thought about those sort of things where you can define things in a concrete way and then parameterize them in the model, which we can control afterwards?
Yeah, so good question. Could we find parameters that are good for controlling these models? Right? And I think it might be possible. People have developed some techniques to discover parameters that can move some of these generative models in particular directions. But I think the question is, how interpretable are those parameters, and how do you convey what they mean to your users? And that's maybe a little less clear.
Any other questions? No, I can have a question.
Okay.
I really like the idea to have the spatial control of the images when people usually just think about how to do prompt engineering. And that is for the image-based image level creation. And then, if we want to further proceed to video level creation, what kind of any other control, whether spatial or temporal, you think is most important for video level of creation? Like if we want to create some very aesthetic, video and movie.
Yeah. So it's a great question. How would we make a control net for video?
Yeah.
Right? I think one thing that lots of people are trying different ways of doing this. We're trying some ways to do this. The one thing that I will argue is that for video, text input is really not enough. Okay, so these methods that take text in addition to other videos that can help control the output, I think those are much more promising in the long run than simply doing everything by text.
Next again for the talk and thoughts.
Thank you, Professor Maneesh, for the great talk. Now is time for introducing Professor Ivan Laptev. He is currently a visiting professor at MBCUI at Abu Dhabi. He's on leave from INRIA Paris, and he's also serving as the head of research at Vision Labs. Professor Ivan has already shaped the field of visual recognition of human actions and interactions with his seminal work. He has authored over 150 technical papers and has assumed numerous roles as area chairs and program chair, including his current role as program chair of this current conference. Professor Ivan has carved his way to a remarkable career. His recognitions include prestigious ARC starting grant and the Heilbron Prize. On a personal note, I have admired Professor Ivan's work since embarking my PhD journey, making today a particularly special moment for me. His contributions have not only shaped the field, but also have guiding inspiration to emerging research.
You're all. So I will want to make disclaimers straight away. So I'm not going to show fancy generated images, but I'm going to show some real videos. And this video in particular, actually, I've been showing for a long time. So the labels you've seen here, so they are not automatically created because this video was done 15 years ago. And why I play it here, so I want to make the point. So there are many things which I've used this video to argue that vision is hard. And actually, most of it, what we see here, the labels on the left, so it's you consider it to be solved or almost solved. So on the right, there is still same video, but something more complex, and I'm not sure we yet understand how to handle these cases, and I'll get back to this one. Okay, so in this talk I want to very briefly just say how we got to the left part, and where we are now, and maybe what do we need for to reaching to the right part, to solving these problems we just opened. Right, so just scrolling back 20 years ago, so that was the video understanding at the time of my PhD, and so quickly it went to analyzing more real videos, and so that's what just 15 years ago, still very, very far away. Also, why I'm doing here, so while doing this work, so it was great to understand that we can actually recognize actions in realistic videos like that, but the training data was straight away was a problem, because how do you annotate such actions in real data? You need to watch thousands and thousands of videos. So there was this idea of looking at video and text. So I think this maybe came even before people started to look at text and images closely, so because of the annotation issue. And scripts, indeed, video scripts, movie scripts in particular, indeed, they can be very detailed, they can describe lots of things, so why not trying to use this as a supervision? So that was the idea at the time, but this supervision is not for free still. Well, it's free, you can download scripts, but still there is much ambiguity, you don't know the character, like if the script mentions people, if scripts mention actions, so there is no correspondence, no spatial correspondence, and very weak temporal correspondence. So that's was one of the problems to solve. And now, looking back, I can say that we can call this small language model. That's what we were doing at the time. That's already like 8 years ago. So basically, so you had text, you had in like frames, and then you had to associate them together. So during training to learn a model which would produce the spatial and temporal correspondences between entities in the text and in the video. All right, and that's actually this small language model. They brought us quite far. So what you see here is an example of a video from some 8 years ago, where the program was just given the movie and the movie script, and then it figured out automatically who is who in the video. And by the way, so here the green boxes, they are correctly recognized as not main characters of the movie. So main characters of the movie are correctly recognized and without any manual intervention. So just text merged with videos. Right, and then of course, like what in many cases what brings us to further improvements, even if you love models and math and modeling things. So usually it's the data scale. So data scale, as we know now, it's important everywhere. So one step forward was actually away from movies, because movies is the limited resource. One big resource of language and video, which actually provides good, now we know that it provides good pre-training and good resource for video understanding is our instructional videos on the internet, because they are many and because they are narrated, and when people narrate narrations in these videos, they actually describe what people are doing. This is exactly what we would like to learn for our models. All right. Okay, so a few just steps how this data set was created. Again, there was almost no manual intervention, and so it was relatively easy. One student project already 4 years ago to collect data set of how to 100 them of 100 million of small videos with attached text to it. Okay. So and okay, so by that time, still the manually annotated data sets are great, big, but still like 3 orders of magnitude smaller than what we were able to collect in this automatic way. And now, so for the model, so the model now is very classic, so similar to Clip and to other types of models, where we have a text encoder, video encoder, and in this case, actually, both video encoder and text encoder were trained from scratch, but on this huge data. And what also nowadays may be less surprising, but what was really surprising just 2-3 years ago is that this simple model and huge data, so it was able to give us performance which was way higher than anything what we were trained on manually annotated data which existed at that time. Okay. So basically, or self-supervised, weakly supervised, unsupervised, whatever you call it. So learning for video is really efficient because the amount of just manually annotated data is so small, and self-supervised learning can bring you very far. Right. So one thing which was particular with this model is that the text encoder was trained from scratch. Again, that maybe brings me to the main meat of this talk. So the text encoder is trained from scratch. So now, of course, going from small language model to large language model, what can they buy? So they can exploit knowledge which is already in the text data, which they were trained with, right? And it can also compensate for the data in the video. So it's natural to not to train text, but to exploit the knowledge which already exists. And that's what we've done in this work, was in Marc's last year, where we should try to, this is the problem, is video question answering. So this is where you give a video, potentially a long video, you ask a question, like some question about the video, and the program is supposed to provide you correct answer. So that was actually very open vocabulary video question answering where you don't have multiple choice. So the goal here also was to avoid annotation whatsoever, manual annotation, and just train it from available video resources. And you can do this from just whatever data you have, but it will be very hard because the data is very scarce. So on one side we try to just exploit non-relevant video text data which already exist, and in addition exploit text large language models which are also been pre-trained without the video. And the model looks like this, so it's actually not complicated at all. So it's there's a vision encoder, text encoder, tokenizer, what you see here, one detail, so the clip encoder, text encoder is the word at that time was one of the good ones. However, well, if you just put a text encoder on top of vision, you need to somehow marry them so that they talk to each other, so adapters helped. And one particular lesson from this work was that probably because of the not sufficient vision data, so freezing the language model is very important, otherwise the model will forget. All right, maybe I just jump to the some ablations which strengthen this point. So like, if you don't use language model, the performance is horrible. Okay, so you see here. So language model brings you to a high level, but then so the question is freeze or not freeze, and not freezing probably means in this case that the overall model forgets what the language model knew in advance. So it was useful to freeze, but instead to do adapters and adapt just train a few parameters to improve the model. Right, so state-of-the-art comparison, so it was good. Right, and now so to more recent work, which put it together because they share the same spirit. So we want to use as little manual supervision as possible, but instead compensate the lack of this supervision by pre-trained language model. And now for a bit different problem, which is a video captioning. It's not just video captioning, it's a dense video captioning, which means that you have a long video and you're supposed to produce text for different parts of this video, but also localize this text. So it's both, like if you think of image understanding, so this would be maybe this would correspond to segmentation and captioning the different segments. Okay? So it's basically the same analogy which we want to do in time, right? And so we are not the first to do this. There are plenty of work doing it. Most of them, they're two-stage. It means that they first segment some hopefully interesting intervals in the video, and then given this interval, just do the captioning, which is as drawbacks because if before you start captioning, maybe your idea of what is interesting, what is not interesting, maybe it's bad, right? So what you probably want to do is to do it all together, and also two-stage models, they are not differentiable usually, so if you want to use it as a block to use some other system, backprop through it, then it's better to have it just one stage. So that's was the motivation for this work, and the implementation actually is, can you see here on the right? So we have a transformer model which in once basically looks at the video and then it produces a string which contains both the boundaries. So you see here, it's, the string contains both the temporal boundaries and the text, and it's just one output sequence. So there is no difference. Just some tokens become timestamps, and some tokens become word. So how was this done? Again, so that was using the using inside the large language model, which was the T5 based model, and it was pre-trained on YT temporal 1 billion data set with 80 million videos. So By the way, yeah, so the problem is captioning. There are not many captioning data sets. So how do we actually, what data do we train it from? So this data set, YT temporal 1D, so it doesn't have captions, but it has narrations or just speech. So speech is well localized. So you can just we do transcribe the speech, and we have temporal boundaries. And basically, that's our data for pre-training. So we don't have big data for captioning, but we have big data for speech transcription. And that actually helps a lot. So there are two losses inspired from text models, of course. So there's a generative task that will predict the next token, but also masking task where we try to fill in missing information. Okay. So the benchmarks, right, and here are some quality results, what the model can do. So it provides pretty good, good descriptions in many cases, not in all cases, so the problem is not solved. So this is Hugo Caselles-Dupré, but it also works for many other videos. So the data, of course, it's biased towards the data it has seen during training. So these are often web videos, including instructional videos, sports videos. So it's not, may not or always work on many data. So one more recent work is it's actually a more data set paper, so the data set track, where continuing the captioning part. So there is on YouTube, there are many videos which have so-called chapters. Chapters is chunks of a video which were annotated by video creators to facilitate people to browse and to search. And surprisingly, there are plenty of these videos, and so we have collected this as a corpus, and in this paper shown that training on this task, which seems to be quite, when you see the chapters, text corresponding to chapters here, it's quite sparse, sometimes very vaguely related to the visual content, still because of probably because of diversity, and the size of this data actually helps to produce better captions, and the data is online, so you're welcome to use it. So let me finish with a few slides, which I think relates to this kidnapping scene, which I mentioned at the beginning. So why can't we recognize kidnapping scenes? We can. So what I would argue, and this seems to be, people agree that we are pretty good at analyzing video in the short term, right? So both, of course, objects, one frame, you don't need video, but then even for many actions, you don't have. You don't need many more than one frame. However, there are some longer-term concepts, or say if you, obviously there are questions you can pose, or there are concepts which span not just 2 frames, not 2 seconds, but maybe the whole movie. Okay? So the movie could be 20 minutes, 45 minutes. So the long-term video understanding, this is a challenge both for models, because they usually just consider videos at a short period of time, and results also. Results are pretty bad so far, but also the data, because if you have longer videos, it means just to have more instances of it, so you have a huge number of frames. So I think this is one problem which is open, and this is something to claim that we do understand video. I think this should be addressed in the next few years, and hopefully we'll get better results. Another one is embodied video understanding. So here are some examples. If you give a computer just a frame of a video and try to, well, for us it's obvious what may happen in the scene, but for current video models, or image models, it's very hard. So we don't. And why is it hard? Probably, well, one reason is probably because we have a good connection of language and video, but connecting pixels to physics, to embodiment, I think, okay, actually we don't have data for this, we don't have much data for this, so this is probably if you would have data that would also be working very well, but for the moment we don't have obvious data, obvious approaches that don't work, and that's why it makes this problem hard but also important for many applications, including robotics. So with this I want to finish, and this is just the summary.
Thank you, Professor Wang, for your great talk. We have time for a couple of questions.
Thank you very much. I lead the group at Prime Video in Amazon, so this is like our day-to-day. And thank you for giving your insights. What I'm interested in is you have got text and video together. Have you tried cross-model with audio? And did it give better results, or that was just not useful because you had text already there?
It is useful. Other people have tried this. We didn't try it. For whatever reason, maybe we are lazy, maybe we thought it would not bring enough, maybe it was not, but yes, it does help. Depends on situations, of course, depends on the kind of videos you have. And actually, yeah, there are works, recent works, which forget about text and just try to do a video and sound correlation that it brings signal, definitely. And it will bring signal here as well. How much? I think not maybe so much on average, but in some situations it can bring much.
Thank you so much for the talk. I have a question about the future directions that you mentioned, like Laptev video understanding being a big unsolved problem. And it completely agree with that. Where do you see large language models being used to address this problem, and what are some of the ways in which you do?
Yeah. So actually, these examples I've been also showing them for a while. Turns out, just a few days ago, I described the scene by hand, put it in ChatGPT and asked what will happen. It is pretty good at it. So I think there is a very straightforward way at least to go forward and do something with these type of scenes. It's not sure. It's not sure how far the language will bring us, even embodiment, but it definitely knows things about it.
Okay, because of time, we have to cut here. But thanks again, Professor Ivan. It was a great talk.
And we continue to introduce our next keynote artist speaker, Ella. Ella is a filmmaker and a researcher, the founder of the film production company Kusama Films and Architecture. Interdisciplinary practice that integrates essential between technology, cinema, and politics. Let's welcome.
So hello, it's a pleasure being here because I come from the artistic side, so I think it's great, and thanks a lot for the invitation because I think there are a few opportunities that artists and the technological side can discuss together how the technology you're building we are using. So I hope with this talk we can start a conversation. So my name is Anna. And I'm the co-founder founder of Artefacto. We are an independent creative studio based in Barcelona and Bogotá. And we work around 3 fundamental pillars: learning frameworks, film production, and some applications we are developing. About the learning frameworks, we are mostly committed to promote advancing knowledge and skills in the cinematic and technological fields, with a particular focus on artificial intelligence. To achieve this, we've developed these frameworks with many universities. Also, our films that we've developed has been in major film festivals, and we strive to leverage cutting-edge technology in our project, transforming the landscape of visual storytelling. And last, we are developing some applications that comes from our own needs, because we have technological engineers in our company that help us developing some tools like, for example, screening, that is designed to facilitate real-time audience viewing during pre-final cut stages, or knowledge boxes, which is addressing a common demand among producers for easy access to understanding, organization, and for calls, festival, grants, and mostly in Europe. So, the talk about today is, I wanted to start with our point of view in this subject. First of all, my talk today will be more about questions than answers. We have been researching the impact of this technology on creativity since 2017, and our perspective embodies a critical thinking, and I think it's important essential to understand its implications from our artistic perspective, and how this technology reshapes and redefines numerous cultural and social values such as authorship, copyright, probably maybe the valuation of jobs, as well as environmental pollution, which we will address later on in the panel as well. AI cinema. I'm not sure that today we can talk about an AI cinema yet, of course, mostly from our practice. Mostly now we are using this technology not as a language or a medium itself, just like an adjective, like digital cinema or analog cinema, let's say. The goal of this talk is to understand how independent filmmakers are using this technology. So I'm going to talk from this perspective only, which is my perspective. And that's why, to understand how it's shaping, how filmmakers, how artists are using this technology, that's why we made the first AI film festival in Europe, followed from the style of the Runway, who started the first film festival. And we did it in partnership with Sonar and also Runway. And I'm the co-director of the festival, and today I just wanted to understand why it was important to start this festival last year in June. And because we wanted to understand not only how artists are using this technology, and also the implication, political implication, ethical and aesthetical implication. So that's why the film festival had 3 big sections in addition to the film festival, which it was the research with leading academics in the field. Another that we call Fair, which it was a networking event with creatives, researching, and artists. And the Live, it was more a performative side of the event. So now we are preparing the next edition this year in June, so I hope we can see some of you guys there. It will be great. So mostly one of the first challenges that we had when we were preparing the call of the festival is how we can evaluate the use of this technology, and what are we looking for when we are saying, okay, films done with AI. So to summarize, mostly we arrived to this paragraph, that it was really broad, because we really wanted to understand as many users, no? And also we highlighted the work in collaboration with AI models, which we think it's important this also. So you can see it was supervised, unsupervised, generative models, because we didn't want to focus only on generative AI, because of course there are many artistic ways to use machine learning and deep learning models as well. So we open it and we leave it really open, and we ask specifically to be able to evaluate in the formulary that we really wanted to understand the models and the use of this technology. So we were asking explicitly for the methodology that the artists were using. And after the festival, which I will go into today, we realized that because of all the films that we received, our festival is called RAIN, which means Research AI Narrative, different to explore different ways to narrate. So we are not really looking for these more pure aesthetic experiments if they don't come with a narrative approach. So mostly it's this word narrative, it's a central driving force, and we evaluate mostly this technology where it's not only just an instrument that goes unnoticed. We wanted to understand and also visually how it's been used. And so it was looking for this aim of co-creation. Even I'm not super fond of this term. We can discuss it later on because it gives kind of agency that of course it's not happening. But for now, I think, for the broader audience to understand how this technology works, we think this term is important. So our intention, it was for looking for this author point of view and not merely as a technology to streamline processes. So after the experience, we came with a really preliminary attempt to classify the types of films that we received, which it was June this year, so it was like some months ago. So trying to understand the current landscape internationally, because the call was we received films from all over the world. So first, to understand how these visual techniques were used, we just made a base and simple distinction because with the use of pre-trained models or fine-tuning on training. So we will start with the pre-trained models. Of course, they were the most predominant models used, and mostly we are talking text to image, text to video, video to video, and text to video as well. Yeah, mostly. So we came from this first classification that we call genosthetics. Why we call this? Because it's, of course, mostly related with one of the last diffusion models that it's really available to the wider audience, that it's called Gen 1 and Gen 2 from Runway. And of course there are more companies using this technology and like Picalabs, but it's not so broad use, and the interface is not so friendly like Runway, and they are not so well known. By the time of the festival, we must say that this technology was just mostly they were releasing it because it was released in March 27, so we didn't receive a lot of films with this technology. But as you can see, I guess you have seen many videos with this approach. This aesthetic really started more with close to surrealism, with this realm of dreams, imagination, maybe, probably because the bodies were not perfect, so it was how the artistic and the artists were using this technology, using its imperfection, like, okay, it's imperfect technology, so let's use it in this sense. In these last 7 months, you have seen that there are many videos generated with this, and it's going towards the hyperrealism at really fast pace. Mostly they are using also image reference, mostly from Midjourney, and then going to Gen 1 or Gen 2 using different approaches. Of course, you want to control the video. Video to video, it's of course the most effective. It's interesting to see these subgenres of the use of this technology, like for example commercials, remake of commercial, and AI trailers of movies that they never exist. So it's interesting to see how these short forms they are arising with the use of this technology. So this year we are hoping and we are foreseeing to see many of this technology used in the films, because now it's really abroad. It's well known for everyone. And one thing that to remark is that one of the most common styles is Wes Anderson style, I guess because it's really visual and it's kind of easy to and known for everyone. No? So another category of this first attempt of categorize these films we call Infinite Dreams, because it reminds us of first experiments with deep dream technology in 2015. This kind of continuous forward tracking shot built from interpolations of static images as a characteristic of many films that we receive. As an example, okay, the video is slow, but I think it's getting. You can see here Portrait of Jungle People by Eddie Wong, who won the Lumen Prize for Moving Image Award, that perfectly illustrates these new film forms that are raised with AI. The initial sequence of the film delves into a jungle, experiencing the notion of lashness from the continuous transformation of a landscape images. So in somehow it reminds us some of the earliest films, earliest experiments when we were when we were placing the camera in front of the train and just, seeing how life is going through our eyes. For the artist, the methodology that he used, he was using this Diffusion notebook, and he was creating all the images from there. When we had a discussion with him, one of the things that we were discussing mostly on the festival, because we had later on panels with all the filmmakers, it was exactly this difficulty to get what we have in mind. So how it's this prompting thing, it's not the most really easy thing for creators now to create videos still. It's really hard and really difficult to get what you want, and it's not so natural still, because one thing is the instructions that you give to your camera operator, to your team, but trying to do this with a machine, this is still really hard. So it takes a lot of effort and a lot of trial and error and trying to find the best prompt to understand what you what you are looking for, and so you mostly use images reference to help this process. Another example of this technology, of this use, is one movie that we did for the festival that is called Generative Rain. To do this, we use different.
$25 for premium access, or you will never be an artist. Credit card expired, and so does your career.
Kiwi, what are you doing in my laboratory? Boy, that's a tough one.
My film is a symbolic representation of purgatory, which is also the title. It's an abstract visualization of the feelings from the period in my life when I felt the lowest. And I feel that in order for me to get better, first I have to go through these heavy feelings. This part symbolizes the purification process, or the cleansing fire in purgatory, which you'll see. The calmer ending symbolizes heaven, which in turn symbolizes my journey to healing by getting into therapy. And the computer has always been my escape, my safe place, a place to disappear into the digital world. And that's why I decided to collaborate with AI for this project. The outcome of AI is something which you can never have total control over, and which often has an alienating effect, which is similar to that certain period of my life. So that's it. Thanks for listening. I hope you'll enjoy it.
Hello everybody, my name is Adam Cole and I'm really excited to share my piece, Kiss Crash, with you. Without giving away too much, my work creates a metaphor between two of the most iconic symbols from cinematic history. The car crash on one hand and the romantic kiss on the other. And in the process, it sort of raises questions about what destruction there is inherent to romance, but also what pleasure do we sometimes get from destruction. It also purposefully tries to place AI within this history of image production technologies that are meant to arouse and homogenize our desires, and question the way that this technology might extend this tradition from cinema into the future. I hope you enjoy the work. It's part of a larger installation, which you can look up at kiss-crash.com, and enjoy the show.
This idea that human connectivity is very deeply connected to our hands because we use our hands to materialize our ideas. The project started with real human choreography, Irina's choreography and dance performance that we did motion capture of, and then I transformed it in such way so that her movements do not represent the movement of a human body, but the movement of human hands. And why hands? Well, I think that there's so much complexity in the human hands that basically their complex movement and dexterity can mirror the movements of the entire body.
I think Irina might be in the room right now. Irina, are you here? All right.
Hello everyone, probably you can see me. So I am a choreographer and creative director for film that you will see next. We created it with Neko, Dr. Formalist, and as a choreographer I had the task to find new forms for dance movements, and I had the task how to find new solutions between 3D animation, AI art, and choreography, and how to change the form of human body, but to remain it still as a movement bodies. So hope you will enjoy and find interesting our artwork. Thank you so much.
right? Thanks everyone for staying with us until the end. And sorry for the toolbar, it wasn't part of the clip here, or the video. So we'll now announce the winners of this year's edition of the AI Short Fest. Each winner will receive a cash prize of $500 and the official laurel of the festival. So the first award that we'll announce is the Frontier Award, which rewards the most innovative and audacious film. Our winner for this year's Frontier Award is Idle Hands by Dr. Formalist and Irina Engels. So congratulations to you and Irina. So the second award recognizes the best short overall. This year's best short award goes to Kiss Crash by Adam Cole. So unfortunately Adam couldn't join us today, but we'll make sure to inform him shortly. And the final award is actually your award. I don't know if you guys had time to, there should be a QR code right there. Yeah. If you want to vote, I'll give you just a few minutes. First, I'm gonna thank again our sponsors of the day, which are Taika Labs. They have a lot of t-shirts here, so feel free to grab one after or just later in the day, whenever you want. Choust and AI Film. So thank you very much for them. You can applaud them as well. All right, did everyone in the room vote, or do we need to wait for one more minute? All right, I won't show you the exact stats, but this is very close. So any vote could count right now if you have a favorite. All right, I think we now have a winner. Or no? Okay, no, we do one. All right, the final award. For this final award, you have chosen to honor, drumroll, Ostature by Derek Brenscombe. So. He's not here today as well, but we'll also keep them informed about his new prize. Well, thank you very much again for coming with us today. We just want to thank everyone here for coming here, and also all the people who made this possible, including Charlie, Leon, Sharon, Sehi, and many more. So thank you very much, and feel free to grab a t-shirt now. Thank you very much. And feel free to stay for the paper presentation that's coming next. Thank you.
It's interesting to see how criminals
וואי, שווה. אבל אולי לא כדאי לשבת לידו. אני חושב, לא שאני חושב רק לפתוח לפטופ. דווקא לך, מה שווה? אתה רוצה? סרטיפיקט. טוב, יאללה, מה נשב? נצחק קצת ליד המצלמה, אתה שווה. אז בוא נשב שורה אחורה.
Hi everyone. We will start the paper presentations in 1 minute. Hello everyone, welcome to the CVEU 2023 workshop, and this is Yuwei, and it is with great pleasure to host the following paper presentation sections. And this year we have received a total of 28 submissions, and after careful evaluations by our committee, we have selected 6 outstanding papers to be awarded with the oral paper award. And congratulations to all the authors for their exceptional work. And we are glad to invite 5 of the paper authors to give an on-site presentations here at the workshop. And each presenters will have 5 minutes to give their presentations, and following by a 2 minutes Q&A. And we will try to stay tight to the workshop schedule, so please try to do not surpass the time limit. And I will remind you if the time is running out. So let's first welcome the first speakers to present their paper. Is their progress in activity progress predictions. Let's welcome.
After all this video, I don't know, this is not going to be as exciting as all the stuff you just saw. Let me try to do my best again. So I'm presenting this work on progress in progress prediction. And I'm the second author here on this work. The real work was done by my master student in France, and all the hard supervision work was actually done by Sylvia. I'm just one presenting the work. So I'm talking about progress prediction in video. And this is the task that you want to do online. So you get, it's an online task, you get a video that's playing, and you want to predict how far in are we? How much progress are we making? This is here the curve that you see. The ground truth here, there will be linear, from 1 to the end frame. It's an online task, so you don't have the end frame in the beginning, so you don't know how long it's going to take. And this is useful, for example, the setting where this is useful for is in the operating room. In the hospital, when they want to see how long an operation is going to take, because the operating room is one of the most expensive things in the hospital. There is some research on this, and there are some challenges here. So there's no clear activity start and end point. There's appearance variation and very much variation in the length. In this paper, we analyze how well current methods do and if it's possible to do this at all. There are a few methods that try to do this. So I think one of the first is ProgressNet, that takes kind of VGT backbone with two LSTMs. There is RSDNet that takes ResNets with an LSTM. And there's the UTE that takes 3D convolutions and ending in a single embedding at the end. So these are all published papers trying to work on the task of progress prediction. We added two baselines of our own, so the ResNet 2D and the ResNet LSTM. So the ResNet 2D is just a simple ResNet, 2D output, one frame in, progress prediction out. The ResNet LSTM is we add an LSTM on top. Then we add some naive baselines that will be static, just predicting 0.5 all the time. That's going to be not so good. Random is going to predict between 1 and 100 all the time, which should be even worse. And baseline based just on counting the number of frames. So we don't look at any visual information at all, we just do frame counting. And then there's three data sets that are commonly used in this setting. So there's UCF 101, the breakfast data set, and the Codec 80 data set. Now this is a very complicated slide, and I hope that I can spend most of my time explaining this. I'm looking at organizers. One thing to notice here, there are three groups. Here is the UCF 101 data set, here is the breakfast data set, and here is the other data set. Then you see here three lines. One is completely random. This is, the second line here is always predicting 0.5, that gives you 25% error. So what you see on the y-axis here is the mean average error. And here, at 14.2% for this data set, that's just counting frames. That's just a very simple baseline where we just look at the length of the video. We don't look at any images at all. We just do frame counting. And we have the three data sets. We have these straight lines are the baselines for all these three data sets. And what you then see in the bar plot here is these learning-based methods. And we have two variants. So okay, here's the static 0.5. This is random. Frame counting, we have for every bar, we really give the video, so we give it the full video input, but we also give it an input where we just change all the visual input with random noise. So there is no visual signal to learn from at all. And then you can see how well they do. So you would hope that they do better than just frame counting. But you see on UCF 101, okay, this one does on bar. This is all worse. So on breakfast, it all does worse than just counting frames. Here on the Codec 80, you see this model here, using the full video, does slightly better than frame counting. So, one thing to take away is that you should always use very, very simple baselines in your paper to compare against. You would hope yours is better than frame counting. Okay, can we do better? So, let's then, if the model overfits on the full video, let's just give it segments. And based on the segments, we force the model to use the visual information, at least we try. And then again, here are the three baselines. And we also give it the frame indices as input itself, so that the model itself can actually learn to count. And what you see, it's still actually not much better than the counting baseline. So, can these models count at all? So we made a data set where we can be sure that there is visual information that relates to the progress. So we made a progress bar data set. And that's here the results show, here the error is, well, around 2-3%. So there the models do quite well. So the models can do it, but not all the data sets are suitable for it, and they should always compare to a very simple baseline. Now, to take away, there are some limitations. We only did 3 methods and 3 data sets. The progress net results we were unable to recreate. So the question is a bit, are we really making progress prediction? End of the paper. If you have any questions, I'd be happy to take them. Thank you very much.
Let's see if anyone has questions. questions. And so that's thank again for your excellent work. And that's thank you very much. Let's welcome the next speaker to invite their work, Position-Aware Transformer for Dense Multi-Label Action Detection.
Hi everyone, I am Fabian and I'm going to present our work at Position-Aware Transformer for Dense Multi-Label Action Detection. In action detection, we aim to determine the boundaries of different action or events occurring in an untrained video. Action detection obtains essential contents from various computer vision applications, such as video summarization, video highlighting, sports analysis, and healthcare. In comparison to a sparse label action detection, where a single action occurs in each time step, multi-label action detection is quite more challenging, because as you can see, several actions can overlap at the same time. To tackle this challenging task, we require to learn short and long-term temporal relationship among different actions in a video. With the success of Transformer in modeling complex and temporal relationships, the recent approaches design hierarchical-based transformer to learn temporal action dependencies from multi-scale temporal features. These networks design a hierarchical structure, including several transformer layers, such that the output of each layer is downsampled and given as input into subsequent layer. However, these networks lose positional information, which is essential for robust action detection. Because first, the self-attention mechanism is orderly invariant and it uses positional information. Second, when the self-attention embedded in a hierarchical structure, the issue becomes worse. The issue becomes worse, and to address these challenges, we introduce PAT, which embeds relative positional encoding in the self-attention layer and it employs a non-hierarchical structure to extract multi-scale temporal features for action detection. PAT has a video encoder which encodes an input sequence and video sequence into a sequence of input token, and three main modules: fine detection, coarse detection, and classification module. In fine detection, we process the whole video sequence to learn a fine-grained representation of the video for coarse detection and classification module. In coarse detection, we learn different range of temporal action dependencies from fine-grained features, and then in classification module, we predict action probabilities from the output of fine detection and coarse detection. I should note that in contrast to the current approach, which suffered from using multiple downsampling processes, in CDM, our coarse detection module, we use a non-hierarchical structure to extract them. And to design both fine detection and coarse detection module, we use our proposed RPT, Relative Positional Transformer block, which embeds relative positional encoding in the transformer to preserve more positional information. We evaluated our method on two benchmark datasets, and as you can see, our method improves the state-of-the-art result by 1.1% and 0.6% mean average precision on Giralt and multi-Thomas dataset respectively. However, in addition to mean average precision metric, we also use the action conditional metrics to evaluate the performance of our method. As you can see, our proposed method improves the state-of-the-art result on all action conditional metrics significantly. And also, our extensive observation studies shows that the impact of the different parts of the network. Here you can see a visualization result of our method on one sample of Giralt's dataset. The blue tag shows the grand truth level. The green one represents the prediction by our proposed method, and the red one shows the result of current state-of-the-art method. As you can see, our proposed method has a better overlap with the grand truth level, and also it detects more action instances. So, in summary, our main contributions are introducing the idea of leveraging positional information in transformer for action detection, designing a novel non-hierarchical structure, transformer-based structure for action detection, and we also achieved the new state-of-the-art result onto the benchmark dataset. And thank you for your attention.
Thank you for your work, and if anyone has questions, just feel free to raise your hand. Yeah, okay. So let's invite the next speaker. Okay, the next speaker, their paper is expressive talking head video encoding in style down to latent space as well. And you can just use one computer. Yes. Let's see.
Good afternoon. I'm Fabian from the Institute of Maryland. Today I'll be presenting expressive talking head video encoding in Stargate and latent space, which is a joint work done with my supervisor, Dr. Caselles-Dupré. Starting off with the motivation, existing face video reenactment approaches fall short in capturing the fine, detailed, and expressive facial features. For example, lip pressing, mouth puckering, mouth gaping, and wrinkles, which are not captured in most reenactment methods. And also, they are limited to low resolution. Being able to capture these expressive facial features at high resolution is crucial towards improving realism in reenacted videos. On the other hand, when we consider Stargate 2 latent-based editing techniques, they focus mostly on generating plausible edits of static images. So in this work, we try to bridge the gap between high-fidelity image synthesis or manipulation and face reenactment of fine, detailed, expressive facial features. So in this paper, as I mentioned, we are proposing a Stargate 2-based approach for high-resolution face reenactment with focus on precise reconstruction of expressive facial attributes. Here, a given video is encoded in an extremely compact encoding scheme, which uses a single identity latent and 35 parameters per frame. In this work, we automate the latent space editing process to capture the facial attribute information. So this is the multi-stage pipeline. Initially, given a video, we pre-process to satisfy the alignment requirements of Stargate 2. Then we use an off-the-shelf encoder to transform the aligned images from the pixel space to the latent space. Thereafter, out of the inverted latent spaces, inverted latents, we choose one latent which would be the anchor for the next steps, which has the best identity and the near frontal head pose, basing the entire video reenactment using a single identity latent, not only reduces the rendering data requirement, but also minimizes the identity variation across the frames. As the next step, we encode the head pose on the style flow layer space by scanning the yaw pitch space using an optimization-based approach. As the next step, we encode the facial deformation with respect to the head pose adjusted identity latent onto a subset of the style space, which consists of 9088 dimensions. The encoding that we use is merely a subset of it, which consists of only 32 parameters. We show that the 32 parameters or the 32 indices in the style space is sufficient to represent the complex facial details. So here we use the index sensitivity for the choice of style space indices, as well as to define an index-specific learning rate during the optimization process. At the end, we use a single identity latent and the 35 parameters per frame, which will be passed to the StyleGAN2 generator to get the reenacted frames. Let us look at a few qualitative examples. So this is an example of same-minded instances where you will see the other method has blurred details and several artifacts where our method successfully captures it. This is another example where you could see the complex facial attribute of lip pressing, which the other methods find it hard to capture. Since we use a modular approach, we could replace the identity latent with the identity of a different subject, which would facilitate puppeteering or cross-identity reenactment. Here you could see the baseline methods has several artifacts. And here you could see the eye gaze is successfully captured across it. This is another example of cross-identity reenactment in comparison to baselines. Quantitatively, we achieve state-of-the-art performance compared to several other algorithms, reenactment algorithms. So, moving on to, in conclusion, what we propose an end-to-end pipeline based on StyleGAN2 for expressive video encoding while using just a single W+ latent at 35 parameters per frame, which amounts to just 0.38% of the entire latent space of StyleGAN. So, to the best of our knowledge, we are the first to automate the latent space editing to capture the fine, rich, and complex facial deformations, and to propose an extremely compact latent-based face video encoding scheme based on StyleGAN2 enabling reenactment. So, thanks a lot. That's it from me today. So, thanks a lot for listening.
Thank you very much. If there is any questions for this paper. Okay, so thank you. Let's go to the next paper. The title is Enhancing Text-to-Video Editing with Motion Map Injections. Let's welcome the authors.
Nice to meet you. It's an honor to be it is an honor to be able to present here. And my name is Song Jo from Jugyeong National University. This presentation explains our paper in its text video editing with motion map detection. Recent advancements in image generation and editing are attributed to research on text guide diffusion and Recent advancements in image generation and editing are attributed to research on text-guided diffusion and large-scale language model. Prompt is one of them, which presents text-guided image editing that controls the relationship between the prompt text token and the corresponding image pixel with the attention box. Prompt demonstrates three editing, includes localized editing achieved by replacing a word, global editing achieved by adding a specification, and even the ability to control how much a word is reflected in the images. Diffusion model research has extended to text-guided video editing tasks. Since a video consists of several frames, unlike images, it should be edited in consideration of temporal information. Many video editing algorithms use fine-tuned image diffusion model or zero-shot method to edit video considering temporal information. Because the image diffusion model was trained on text-image pair data set, it is not good at estimating the attention map for prompts containing motion. As a result, it is difficult to perform appropriate attention control for the prompts, which reduce the capability of editing videos. One solution is to estimate motion information explicitly. The core here is motion information, but before that, let's check out this image. Can you find the moving car in these pictures? And now? So we can identify motion information present in video but absent in images. We can also make use of it by optical flow. Optical flow is the information of pixels that have moved between frames of video. With existing state-of-the-art optical flow estimation network, we can obtain highly accurate motion which can be injected into video editing model. Now, I will explain the overall framework of our proposal motion map injection module and the method we employ. First, input several video frames, the source prompts, and target prompts to the text video models. To estimate the motion, the frames are input into the pre-trained optical flow model, and as output, an optical flow containing motion information is extracted. To use only the magnitude information of the optical flow, it is converted into a motion map by applying L2 normalization. The pre-trained text-to-video model computes the correlation between the input frames and the source prompts through the cross-attention layer. To enhance the entire attention using motion information, we attempt to calculate the similarity between the attention map and the motion map by introducing the NCC function used in template matching. The calculated score is multiplied by motion map, and then the motion information is injected into the entire prompt by adding it to the attention. Lastly, we can enhance the attention of the motion prompt by directly injecting the motion prompt into its attention. Afterward, text-to-video editing is performed using the enhanced attention map. Let's check the result through the figure. We can observe that after applying NCC and directly injecting motion map, the results appear more realistic compared to when we did not inject the motion map directly. We conducted experiments for our module based on 3 text-to-video model, which are video P2P, width to width 0 and height 0. Yeah. We evaluate our module with 3 metrics. When we add the proposed MMI module to 3 models for comparison, we can observe improved results. This table shows the user study result. We asked to choose a more faithful one between 2 presented videos on 3 criteria. Over 70% of the users choose our video results for all 3 criteria of preference. So we are going to show you our video results on every text-to-video model we try. Each column contains the input video, the output video from the original video P2P models, and the output video from video P2P with our MMI module. In almost all cases, the results of applying our modules are more natural and realistic. Another video P2P examples. Using our GitHub project page for another result, the project page can be accessed via the QR code on our poster. It's there. Yeah. So, MMI module makes improved video editing results in terms of text alignment, vision preservation, and quality. Yeah. Thank you for watching my presentation.
Thank you very much. And let's see if there is any questions for this speaker. Let's invite the next speaker. This work is using large language model for unsupervised step extractions in industrial videos. Let's welcome them.
Hi everyone, I'm Anyi. Thanks to the organizers of this CVEU workshop for selecting our paper, and really happy to be here to present our work. This is work loose using LLMs for unsupervised step extraction in instructional videos. So instructional video datasets like How to 100M and Point have been extensively used for learning multimodal representations, like for actions and steps. However, these datasets are often sparsely annotated. They're often sparsely annotated, like How to 100M only contains task labels, and the Coin dataset has like generic mappings from WikiHow steps, which means that the annotations are sparse and they miss intricate details which are specific to the video. And using human annotators to annotate every video in a large dataset is very expensive and it's time consuming. It often results in annotations which are subjective. So what we're missing is an automatic, linguistically nuanced annotator which can offer dense coverage of steps in the video and can also be scaled to multiple videos of the same task. So in this work, we introduce Luz. It's an unsupervised approach to automatically annotate any instructional video, and it uses large language models to do this. So let me describe how this method works. So first, we've leveraged 2 main properties of instructional videos. One is that they always usually contain a transcript, and 2, all instructional videos from the same task have structural similarity. So we use both these properties to generate and ground steps in videos. So first we group videos based on that task category, like making coffee or making a burger, and clean their transcripts. Next, we prompt an LLM to summarize each of these transcripts and extract the main set of steps in them. Repeating this process for multiple videos results in multiple different sets of steps. However, each of these individual set of steps will still contain some noise, and they might vary despite being from the same task. They might vary across different videos. For example, if you consider making espresso, this is different from making Turkish coffee or pour over, but they all belong to the same task of making coffee. And there could be variations within the same video as well, like some videos might choose to have grind the coffee beans as a step, whereas others might perform this off camera and leave it out. So to get rid of these inconsistencies across all of these generated steps, we then prompt an LLM again by passing it all of these steps and asking it to remove this variance and generate a more general set of steps. Now, given these general set of steps for a task, we essentially want to localize these steps back in the original videos and their transcripts. And we want to get the corresponding video clips for each of these steps. To do this, we use drop dynamic time warping, which is an algorithm for sequence-to-sequence alignment. So here we align the generated steps back with the original input transcript while dropping in between sentences which are irrelevant. Now, being able to drop outlier sentences and as a result the outlier frames is extremely important because instructional videos often have scenes and segments which don't correspond to a step, such as an introduction talking about an inspiration for a recipe or a personal story. So doing this with Loose, we're able to generate step labels and also obtain the corresponding video clips for any video which has a transcript. So what do we do in a case we don't have a transcript? So in order to use Loose for cases where we don't have transcripts, we fine-tune existing video models using the video step pairs that we generated from videos which have transcripts. So in this work, we've tried 3 different video models, video and image captioning models. So learning with distance supervision, Blip2, which is an image captioning model, and Lavilla, which is another video captioning model. The good thing is now our method can also work real time. So we just sample 1 frame every 10 seconds of an incoming video stream and caption this frame using our fine-tuned video model. So here are some qualitative results of our method. So in this example, we show that Loose is able to generalize well across different variations of the same task. So we see 2 different ways of making coffee. One is a Turkish coffee and the other is a pour over. And we can see that using our method, we can generate a very general set of steps and obtain clips from both these videos which correspond to each of these steps. The labels generated by our method are also more dense and accurate compared to other ground truth labels. So here we compare to the coin dataset where the labels are collected by human annotators. So they were given a set of steps and asked them to localize like each of the steps back in the original video. So using our method, we get, for this video on how to make a burger, we get 7 steps, whereas using the coin ground truth, we only have 3 steps. Also, you can see that for steps like form the mixture into patties, this is more descriptive of what's happening in the clip compared to like the step label from the coin ground truth, which just says in the meat. And here's an example of using our labels to fine-tune video and image captioning models. So here we're fine-tuning Blip2 using the labels from our step extraction process. Again, comparing to the coin ground truth, you can see that the labels generated by our method are more descriptive and dense. And again, it takes 3 annotators to annotate a single video in the coin dataset, whereas using our method, we can do this completely automatically and with no human involvement. Then we also use sentence embeddings, a sentence embedding network to find the nearest neighbor coin ground truth. That's the sentence transformer. And this allows us to map back the step labels which are generated by a method to the coin ground truth, and we can see the variation in the output quality doing this. Next, we want to design.
Time is running out, so
Next, we want to design a better method to get rid of outliers, especially like starting in intro frames and advertisements, which often occur in instructional videos. So as future work, we want to evaluate use on dense video captioning as one of the tasks, and we also want to be able to identify mistakes in your user videos by fine-tuning models of our methods. Thank you.
If there is any questions for this paper. Yeah.
now in the context of GPT-4 completion capabilities, so do you have any thoughts on whether this task would be possible with GPT-4, assuming it has the capabilities for video sequences, basically? Do you think that's something that will be doable, or like what will be potential blockers you think that may exist in the completion by?
Yeah, thank you. That's a good question. So I'm still working in this area, and that's like something we're doing right now. So yeah, I feel like whatever prompting we've tried with just like GPT-3 and only text-based models, we're going to pretty much extend it to like models which are multimodal. So you can imagine a situation where you pick some frames in the video and have like, you know, a question corresponding to it, and you can prompt the GPT-4 or any multimodal model with this now multimodal prompt and have it like pick the relevant frames. And hopefully with like enough sort of examples and with few short prompting, it should be able to do much better than just our language only model. And so I think like, yeah, there's like endless list of tasks that we would now be able to solve with multimodal prompting.
Thank you. Okay. Last questions.
Thank you. Actually, I have a question about this data domain. So you have mentioned that this is instructional video. So have you tried, or how do you think it applies to like in general video, like me walking here or I'm talking here? Yeah, thank you.
Yeah, that's a great question. Thanks. Yeah, we've tried it on other videos where you do have speech, like news. It works well as long as there's someone talking, but in cases where there is no corresponding like speech and there's no exact structure to the video, like just a vlog, I think it's more difficult to segment it using the step-over technique. But like one solution to what you proposed is to probably use dense captioning to caption the video first, and then pass your captions to the language model and ask it to extract some sort of like steps from it. But yeah, we haven't necessarily tried this. Thanks for the question.
Yeah, I think we are 5 minutes behind the schedule. If you have other questions, we can discuss with the author after these sections. And at the end of the paper presentation sections, yeah, I'd like to thank our outstanding reviewers. And yeah, I'm excited to announce that yeah, outstanding reviewers are these great people. So that's congratulations and thanks for their great works for this workshop. And I'm excited to announce that after careful selections by our committee, the best paper of the CVEU 2023 workshop is the expressive talking head video encoding style gun to latent space. Congratulations to authors and thanks for their great work. And now let's take a 30-minute coffee break, and our workshop will continue at 4 p.m. And there will be 3 professors to give 3 speakers to give their keynotes, and so please be back on time and stay tuned for the insightful presentations. Thank you. So if anyone can pick up these t-shirts, you can come from pick up t-shirt.
כאילו לא הבנתי כלום מה5 דקות האלה, כמעט כל אחד מהם. חוץ מהאחרון. אלא אם כן ממש בתוך התחום. כן, וגם... ואחד שממש לא מוצלח, דקה האחרונה באמת הייתה טובה.
Tomorrow. That's good. Yeah.
I meant, like, I think one of the logistics guy, he took a phone from one of the speakers because, like, he was just laying on the chair. But now we cannot find the guy. Whom do we ask? The logistics. Yeah, probably one of the. I mean, I can go and find him.
You know about the student volunteer? I think they can help us too.
No, okay. Yeah. Sure.
Okay.
Yeah.
So it's just like text to audio. Primary. Mostly because I want to learn diffusion models say that our trajectory is determined by so the Brownian motion, we know on average, you can kind of like vary. Brownian motion, the variance distribution is still counted. So that's kind of how it's just like, okay. Actually back in order.
Thank you for questions. And if there's anyone want to have a questions?
Yeah, thanks for the talk. So, like looking at the result, it seems that the model picks up pretty easily the camera movements, right? Mm-hmm. And that's something that we have seen like across models.
Yeah.
But I guess related to the question was just asked, like how to maybe model the actual motions that we were hoping to see, like a person running, or like maybe it's related to the non-rigid objects. Because it seems that the data-driven approach is giving us the camera motion pretty well, but maybe not the other motion that kind of we're looking for. So really, is it data-driven? Maybe we just need some like better representations of the inputs, or I don't know.
Yeah, I think again that's a good question. So data-driven would work well if you have enough data, but sometimes adding some kind of like conditional inputs are very effective with these models. So if you're able to somehow get some kind of like motion representations and somehow use that as an intermediate step with these models, that might be a very promising approach. So yeah, I think that approach has a lot of promise.
If there is any other questions? I would like to ask you another question. Yeah, I would like to know what's your opinions about how to comprehensively evaluate and video generation models. Since there is so many models trained on different data sets, but they use clip similarities or FED or some. Well, I think this metric is not very comprehensive. So
that's a very good question. So I think we don't have good metrics for video model right now. That's my personal feeling. And even though there are all these clip similarity or these FID kind of metrics, none of them do justice in really measuring the quality. And even before we go to video, even for image, I don't think we have like good metrics. Like FID can do a decent job, but then it still doesn't really capture like which image is like really aesthetic. And the problem becomes much more worse with the video. I personally, when I work, like what I do is I just like visualize it, like I just trust my eyes. But I definitely think as a community we should work towards developing good metrics, and unfortunately I don't think there are any good metrics right now. And we should aim to develop like automated metrics, not just human evaluation.
Thank you for your answers. And thanks again for Dr. Yogesh. Thank you.
Thank you. Thanks so much.
Okay, now let's introduce the second keynote speakers, Dr. Kfir. And he's a research scientist and a team lead at Snap Research. He was previously a research scientist and manager at Google Research. He is passionate about emphasizing impactful and meaningful visual effects. Today, his keynote will focus on generating personalized content with text-to-image diffusion models. And now let's give our warmest welcome to Dr. Kfir.
Hi everybody, I'm Kfir, and today we're going to see some of the magical avenues that happened in the last year in generative AI. But before diving into the details, maybe a brief overview about myself and my background. So my name is Kfir, K-F-I-R, it's not Kfir and not Kfir. Usually people stack some vowel between the K and the F. The meaning is like lion cub in Hebrew, pretty simple. I grew up in Israel in a small town in the north of the country with like a pretty religious somewhat background. I served in the army for 6 years, in the intelligence force, in the visual intelligence force. I dealt with satellite imaging. It was really fascinating. I did my PhD in Tel Aviv University with Daniel Cohen-Lor. During my PhD, I moved to China, and I've been living in China for I lived in China for 3 years. It was pretty fascinating, and I learned the language and the culture. Definitely miss China. Then I moved to Google. I moved to Google, to the US, and spent there 3 wonderful years at the CCI organization within Google Research, which is led by David Zelicin, who is here. And I just recently joined Snap, and I'm leading the generative AI research effort there. In Google, we did a lot of stuff, but when I just joined, we were focusing on these super utilitarian features that can help people to improve their photos. Specifically, me and my team worked on Magic Eraser. It's a fully automated pipeline that enables you to automatically detect distracting elements in your image and just remove them. And we got a pretty nice press coverage, and this feature was really successful. And back then, we were trying to think how we can leverage generative models to improve people's images, and we were looking into guns and style guns, and we did a lot of stuff in this domain, but then something happened. Then, exactly a year and a half ago, April 2022, DALL-E 2 was out, and basically then started the rise of generative AI. Followed by DALL-E 2, there were many like parallel works that brought to our world these unprecedented results of text-to-image, specifically diffusion models. And we're super excited about it. And just at the time that we were super excited about it in Google, Stable Diffusion was released. And since then, everything is a history, because so many companies just pop out, and these capabilities were approachable. So when we just firstly saw these capabilities, we were trying to think how we can actually use them, how we can actually control these text-to-image models. And when I say actually control, I will give you an example. So this is the first AI-generated magazine cover of the Cosmopolitan magazine. And this is the way it was actually generated. Let me show you some.
White print. This one, for example, was too boxy. Each time I adjusted my prompt over and over again, refining it to try to get the right image. And after many, many hours of trying hundreds of prompts, finally figured out the right one. It was. Here's how it turned out.
So as you can see, prompt engineering is such a big hustle, and it's such a not intuitive tool, right? Why we should like prompt engineer sentences to generate like visual stuff? And it actually became a profession. You can find it, on those like freelancing platform. It's become a profession. People are becoming experts in prompt engineering, but it doesn't make sense. right? What happens if tomorrow, like the text model is going to be replaced with something else? Should we replace our knowledge with something new? So given that mindset, we're trying to tackle two main directions. We're trying to think how we can take these models just to edit images, and I know that now it seems trivial, but imagine like what happens like a year and a half ago. How we can start from an image and then, for example, make this boulevard less crowded. Or, and the second step, how we can guide the model with specific visuals. I don't want to generate a general person, I don't want to generate a general dog, I want to generate my dog. How we can customize, how we can personalize this model, this is another question we're trying to answer. So for the first branch, for the content editing, when we just got these models and trying to play with them, it was pretty clear that it's really hard. Why hard? Because we generate a Chihuahua dog running on the beach, and then we just stack this like adjective white, and we try to make this Chihuahua a white Chihuahua dog running on the beach, and this is what we get. And even if we try, you know, so many seeds, try, this is the closest thing that we could get at that point, and it doesn't make sense. That's why we published Prompt to Prompt. This is, I think, our first work. It's a big avenue in the generative AI domain. And Prompt to Prompt enables us to edit images by just editing their corresponding caption. So, for example, you can take a photo of a cat riding on a bike that was generated by your model, and you can replace this word bike by the word car, and to get this thing, you can make your cake more decorated with jelly beans. You can just turn your image into a children's drawing of the same thing, and you can make the boulevard less crowded, as I just mentioned. So just to give you some intuition, I know that probably most of you are aware of how diffusion models work, so I don't have to tell you that you start from noise, and gradually, you turn this noise into an image based on the guidance of the text. But I think when we first saw these models and we were trying to analyze how to control them, it was so confusing and fascinating because the process is so convoluted, right? It's like so many like iterations, and you have the prompt, you have the null prompt, which will play a key role later. Each block in this unit contains like the residual network, the self-attention module, the cross-attention model, and we didn't know how to start with controlling this thing. But one obvious thing was that in the cross-attention layer, this is the first place where the image features are coming into interaction with the text features. And the mechanism is pretty, simple and familiar, I guess. It's attention, you get the image input, which are being converted into query features. Then the sentence is, like each token in the sentence is converted into a key feature. And then we multiply them both to get some attention map. And this attention map is multiplied by the values that are coming also from the text. One of the first things that we've done is to visualize those cross-attention maps. And this is what we get. And I was super excited to see this because I think it's the first time that we were actually, we could interpret deep networks. Because usually, it's like a black box and you train weights and you get something, you don't know how you get it, but here we can actually see that each of the words, especially the nouns, has a visual interpretation within those like deep representation. And it happens from the very beginning of the diffusion process, if this is like the diffusion time. So utilizing this finding, we can now just fix the cross-attention layer after we generate. Imagine that we generate one image with the text. We can now fix the cross-attention layers, and we can generate again and again the same image with different noise, but now we can fix the semantic composition of the image. And this is very cool. It's one way to control the generation and the semantic layout. Another interesting thing is we can do the same thing even if we generate the same image with a new word. So we imagine that we want to generate a bunch of different cakes. Lemon cake, cheesecake, monster cake. So if we just replace the word, even if we fix the noise, we get a different cake each time. But if we fix also the cross-attention layer, we get the exact same structure, and it's kind of a semantic texture transfer, right? We just replace the texture and we get the exact same structure of cake. Another interesting thing is that it's a diffusion process, so we can fix the attention layer through all the process, but we can also fix it just for a part of the process, and this is how it looks like. If we don't fix it at all, on the leftmost example, you can see that if we try to change this image of a cat riding on a bike to a train, we get a totally new image, a new image of a cat riding on a train. And if we fix it through all the way, we get an image that has high resemblance to the original image. And you see that the train is kind of squeezed into this shape of the bicycle, but we can play with it. It's a trade-off between how much fidelity to the structure we want and how much fidelity to the semantics. So prompt to prompt was nice, but it worked actually only on synthetic images. Because you have to generate an image, and only when you generate you have the cross-attention layers. The big question was how we can apply it to real images. And then we published null-text inversion. And the idea behind null-text inversion was, let's try to first invert the real image into the model, and once we do it, we can actually now generate this image with this model, and we can do prompt to prompt again. And then we can take this image of the cat and making this cat like a silver sculpture, a tiger, or we can even make it sleeping. So on a very kind of brief high-level overview, the way that null-text inversion work is we start with a naive process which is called DDIM inversion. We just take the simple DDIM process and we invert it. And when we invert it with the main branch, like with the main conditional branch of the diffusion process, everything is fine. Like we can invert back and forth and we can reconstruct the image with this given caption that we provided. But with diffusion model, we have to generate the images with another branch, which is called the classifier free guidance branch, which is important for like editing and reverse generation. And if we do naive DDIM inversion and then we then do the reverse diffusion process with the classifier free guidance component, we get some deviation. We get some error that is accumulated through the process. And the idea behind null-text inversion is to utilize this null-text that is injected in the other branch of the process and everybody ignored, for our work. And we basically optimize this null-text. We optimize a sequence of null-text such that we're compensating the gap that was created here. And after compensating the gap, we can get a perfect inversion of that image. So now, without changing the model at all, we can take this noise that we inverted, we can take the caption, and we can generate our image. And the nice thing is that now we can use prompt to prompt. We can take a real image with a given caption, a man in glasses eating a donut, and we can change his appearance, we can change his expression, we can change the background, we can change the donut to pizza, we can do so many things on real images. So this was another kind of exciting result. Since it's a workshop on videos, so I just want to say that this work has been used for like many use cases also in video editing. One of them just combines prompt to prompt with optimizing one null-text inversion across all the frames to get temporally consistent video editing like this money, which is really cute. And this is another example where, again, we do this inversion per frame, and now we can turn this video into night gradually by just pushing the cross-attention weights more and more, like we do in prompt to prompt. So for the second branch, personalized generation, it wasn't trivial to us at all how I can generate my own dog. I don't want to describe my dog with words. I want to provide a few reference images and now to find kind of a personalized subspace within this model. And I hope that at this point you heard about Dreambooth, but this is what Dreambooth enables back then. So with Dreambooth you can take a few images of your dog and you can embed them into the output domain of the model by fine-tuning the model, and then you can generate your own dog in different contexts and different interactions with the world. You can make him swimming in the ocean, you can give him a haircut, you can put him in a bucket. And it's been a year since we've published Dreambooth, and I'm still super excited every time I see these results again and again. So the concept behind Dreambooth was that with those models that are guided by text and even guided by images. For example, DALL-E 2, you can provide an image as an input. You cannot reproduce the exact object with just even image guidance, and even not with like text guidance. You can maybe change the context based on text guidance, but you cannot get the actual clock. But Dreambooth enables that, and the way we do it is by simply fine-tuning the model. We take a few images of our dog and its class, dog, And Dreambooth basically fine-tune a model such that a new identifier, in this case V, from now on is going to represent our dog. And then in inference, after fine-tuning, we can refer to our dog with this unique identifier V. So we can say a V dog in the beach, and we get our dog in the beach, and a V dog walking in a colorful carpet, and we get our dog. The way we do it in practice is we simply fine-tuning. We keep training the model with those few images and reconstructing our dog when the prompt that is injected is a V dog. But in parallel, what we do in order to let the model not forget the concept, the general concept of dog, and to be able to generate more dogs beyond our dog, we keep training the model with reconstructing other dogs when we provide a sentence a dog. Okay, so two objectives. Please generate my dog when I say a V dog, and please generate other dogs when I say a dog. Since we worked with Imagen originally, we also had to fine-tune the super resolution models, so the fine-grained details of our subject are being preserved. So with Dreambooth, you can take a few input images of any object, and you can embed it within the input domain of the output domain of the model and generate it in a pretty like good quality. You can also take this teapot and generate it in different contexts and even in different materials. You can take your dog and generate it in different, artistic renditions. And again, it's not style transfer, right? We modify the pose of the dog, and we can do so many crazy things. And another very exciting application of Dreambooth is the ability to take a character and to tell a coherent, consistent story with the same character. So imagine, I guess, what was the impact of these kind of things. So when we published Dreambooth, we were lucky that Stable Diffusion was released a couple of days before that, and then Dreambooth was and still is everywhere. We see many creative ways that people are utilizing Dreambooth, and many startup companies that were raised just based on this idea. People are making headshots, stickers, holiday cards, so many cool things. I was really excited, to be able to generate to envision myself, to envision the younger version of myself, in a yearbook, and to see myself as a superhero and like all these kind of cool things. Some other follow-up works that related to video. Again, we are in a video workshop, so this DreamMix work enables us to generate subjects. Sorry, to generate subjects with a few images in your videos. So you provide a few images of an object, and you can generate novel videos of that object. And the concept is pretty similar. The idea is just using a text-to-video model instead of a text-to-image, and in this work, those folks used text-to-video, like the image and text-to-video work. And also animative that was presented here earlier. And the really nice thing about animative is that the concept there is kind of agnostic to the fine-tuning of the model. So you can take your own personalized model and animate it without customize the image to video approach, without customize it to your fine-tuned model. So you can take your own personalized model and now create a video. It's super exciting to see those results. Not so long ago. Where are the challenges? Where are the open challenges in customized or personalized generation? So we have a few follow-up works, but I think still it's not solved yet. Still, to get the best results, we need to fine-tune the model. We need to modify the weights. It's expensive to utilize GPUs, per user, per customer, and to save the model per user. How we can generate multi-subjects? How we can have a dictionary that just grows with time? It's also a very kind of open question. There is a pretty it's pretty limited now for a few 5, 6 subjects, not more than that. How we can make personalization from a single image? There are some works in these domains, but I feel that these are still kind of pretty open challenges. To just wrap up the talk, I want to say a couple of words about Snap, because I just moved to Snap, and I'm pretty excited about the opportunity. And Snap is a great platform with a big user base, where it's a classic place, to have your novel ideas and novel effects, and then let a few weeks later for 1 million users to try it. And the mindset of Snap at the moment is how we can actually leverage and utilize those assets of users, images, videos, in order to generate content that will be captivating for them, will engage them, will be personalized to their taste and assets, and how we can make the camera actually generative. And also hiring, and if you are into some of those open positions as research scientists or student interns, please feel free to reach out, and thank you very much for your attention.
So thanks again for this enlightening keynotes, and let's see if anyone wants to have questions. Just feel free to raise your hand.
For the great talk. So I was wondering, one of the challenges you mentioned is about multi-subject, and you have been trying a lot of the personalization models to try to generate multiple subjects. It's not blending their identities, like it's very hard to control. I wonder if you have any idea how can you leverage, for instance, prompt to prompt with personalization models to kind of specify which areas of the image I want to personalize. So I'm thinking, like, can you leverage like template images and then personalize those template images? Would something like that actually be feasible? Like, do you see any avenue in this direction?
Yeah, so definitely, I think that the idea behind prompt to prompt is to utilize the close attention mechanism to connect between tokens and regions in the image. So if you provide a more strict guidance, when you, for example, fine-tune a model and you say, oh, so this subject should be connected to this unique identifier and this subject connected to this unique identifier, if you add some loss that will make this clear connection, will definitely help to separate. That being said, the capability of the model to handle, even with this kind of guidance, which is really, I would say, the state-of-the-art capability to modify, like to separate subjects. That being said, when we fine-tune, it still seems like the energy, for example, if we think about LoRa, and we try to fine-tune, to modify a set of weights, and connect each subject to each unique identifier, we still see some semantic overlap at the end of the day between subjects. So especially if we try, to embed 100 different 100 different males specifically, we will see that you cannot actually distinguish, even if you utilize the close attention mechanism in the fine-tuning. I see that people are coming, there are some kind of more naive approaches to blend subjects if you have different models for a different subject, and then you do some kind of segmentation, and you paste stuff. This is, of course, more naive solutions that people are doing. But how we can add a new dictionary of 100 subjects into a model, this is definitely helpful.
Thank you for your questions. And is there any other questions?
Hi, thanks for the great talk. So I was wondering if there is any way to incorporate the edition functionality directly within the training of the model, because it seems that most of the approaches try to come up with an editing mechanism that comes attached to a pre-trained model, but wouldn't it be interesting to create one as the default functionality of the text-to-image model, for instance?
So, just I want to verify that I understand. So, like, for example, if we're talking about the multi-subject problem, for example. Yeah. So you can say that. Oh, right. For this, like, the model definitely know more than 100 celebrities, right? So it's all the celebrities like many times. But to get this model, we had to apply like a large-scale training. We cannot do this large-scale training now for every subset of 100 subjects. That's why we have to take a given, large-scale model and to fine-tune it. And when we do the fine-tuning, it doesn't work. Yeah. So if you would be able to, embed everybody in one large-scale training, that might be possible.
Just let's say, for instance, so we had like a video with Rabbit, I guess, that was changed to another style. So maybe if this edition functionality with not with the particular style that you want at this time is done beforehand with training, then maybe if the mechanism is embedded directly in the model, then you can just provide the image in which you want the rabbit to be transformed into maybe. Did you get what I mean?
Yeah, so yeah, definitely. But I think it's correct if the mechanism is like, and the capability is there, right? If we think about people, like I want to generate you, I can maybe invert your image, but I cannot, won't know that it's you, right? Yeah. But definitely, like guiding the process through visual examples, if it's already embedded in the output domain of the model, this is something definitely.
Any further questions? Is there any other questions for them? Okay, let's thank again for this very insightful.
Today we've had great researchers on stage and also talented artists here. For our last keynote speaker of the day, I have the privilege to introduce Dr. Hugo Caselles-Dupré, who is not only a great researcher but also a talented artist. Hugo wears many hats. He earned his PhD from ICCV Paris and INRIA in 2021, and he now serves as a postdoc at Sorbonne University. Besides academia, Hugo is also a groundbreaking artist. With two of his friends, he co-founded Obvious Art in 2018. The same year, they sold Portrait of Edmond Bellamy, the first piece of AI-generated portrait in history, at an auction of $432,000. With this sale, Hugo and his co-founders blazed the trail of a new era for digital art and art more generally. For that, they were selected among the Forbes 30 under 30 in 2020, and since then, their works have been exhibited in many galleries all around the world. Please join me in extending a warm welcome to Dr. Caselles-Dupré. Thank you.
Thanks so much. I needed an introduction because I didn't have one, so that's very great. So today I want to talk to you about basically what we do at Obvious. So we are three friends from childhood that decided to work with AI to create works of art back in 2017. So as it was said, I'm a researcher in that domain, and basically we had this idea in 2017. And so as it was said, also our first series of artworks was a series of portraits. So the one that you can see on the left is the one that was sold at Christie's. It's called Edmond Bellamy, and basically we were dabbling with generative adversarial networks, which at the time were the best algorithms that you could use for image generation, and we were fascinated by their potential, and so we decided to create this series, and then we were contacted by Christie's to do this auction, and so many things happened after that, and since then we've been creating different types of artworks and conducting artistic projects and research projects on generative AI. On the middle and on the right, you can see all the types of series that we created in 2019 and 20 in this era where we were using GANs and working with craftsmen to create artworks, reinterpreting different artistic approaches. Most recently, we did our entry at Danny's Gallery, which is our gallery today, and now we're using all the different type of algorithms that are available to create our series. In this work, we worked on the 7 wonders of the ancient world, and we worked with historians to gather the actual description of the 7 wonders, because besides the pyramids, we can't really know what they look like, and so we wanted to use text-to-image algorithms to reconstruct them, and that was the show that we did last winter. So we did many exhibitions within our different artistic projects in different museums and galleries. And we also work with NFTs. Actually, we've been creating NFTs since before it was hype and a little bit weird with all those monkey stuff that you saw in 2021. Basically, NFTs, there is this small part of NFTs that is not scammy and it's really interesting for digital artists to create their work and to commercialize them. So besides all the frenzy that you've seen, there are many talented artists that are using NFTs to now sell their work in galleries, and it's actually a great thing in this digital art space. So we've been creating those since 2018. We had the chance to be invited to the beta of Super Rare, and we did many different projects with NFTs. We also like to work with brands as well, so I think it's interesting for me to show you that, because all of the algorithms that we saw today, basically we try to use them for artistic projects, and now you can see how by doing different projects with brands maybe, we can showcase some creation that were done using those algorithms, so it's kind of a practical application to everything that you saw today. So for instance, we had, so the video is not moving. So we did a collaboration with the Alpine brands, Formula One brand, who also makes a car, and we did the art car where we invented the circuit using generative adversarial networks, and we did some covering of the car using other types of algorithms, type transfer and different type of generative AI algorithms. More recently, we did a bike for one team of the Tour de France. So all of the different type of rotation that you can see on the bike are kind of the human-machine collaboration between the bike and the cyclist. So we thought it was a cool way to connect to our work, which is also collaboration human-machine, and basically all of the concentric circles are generated. So that's how we use the AI to do it. And okay, so I cannot load the video, but maybe I can just take a quick moment to grab my Wi-Fi. But we did a collaboration with Opéra de Paris to do actually a project around NFTs, and so we were able to create different types of animation that was sold to the different collectors that are interested in opera, so it was a way to onboard them on our creation and on this technology of NFTs as well. And here you can see we used some of the latest algorithms from early 2023 with video initialization and all the types of really great algorithms that you have today. One good thing is that if you're interested in our work, we've been creating for the last 5 years, and there's actually a documentary that was filmed on us during the last year, and so it will be released on Canal Plus, a French TV channel. So it's 72 minutes on our work. So maybe if you're interested, you can check this out in November. So today I want to talk to you also about the research that we do at Obvious. So the idea is that I showed you the different type of artistic project that we conduct, but the whole idea was also to get into the actual research ourselves. So that it is an ambitious project that we had for the longest time, but we needed time to organize all of this, and now we're happy to announce that we are actually creating, besides our artistic studio, an academic laboratory. So the idea is that the creation that we will do in this research lab will be created with the aim of having artistic applications. So I think you can think of all the type of algorithms that were presented in the last presentation, for instance. That's typically the type of algorithms that we are interested in. It's a partnership with Sorbonne University, and we have some public funding of $1 million to €1 million for the next 4 years to work on this. So we'll be hiring as well. So if you're interested in working in generative AI research,